Hey everyone, welcome to this exciting course on SCIKIT Learn. We're about to embark on a journey that'll elevate your data science skills to the next level. Throughout this course, you'll gain hands-on experience with machine learning algorithms, explore data pre-processing techniques, and dive into model evaluation. Get ready for some coding exercises that are sure to sharpen your skills. Trust me, they're super engaging. And hey, don't forget to check the description below for a link to our GitHub repository. That's where all the code will be waiting for you. Stick around until the end too, because we've got an awesome final project that'll really test everything you've learned. So, are you ready? Let's dive in and get started. Machine learning is a fascinating and rapidly evolving field that has transformed the way we analyze data, make predictions, and automate various tasks. Today, we're diving into the captivating world of machine learning, focusing on its fundamentals, key concepts, and practical applications. By the end of this session, you'll have a much better understanding of what machine learning is all about and how you can utilize it in your own projects. So let's jump right in and explore how this amazing technology works and where it can take you. To kick things off, let's clarify what we mean by machine learning. At its core, machine learning is a subset of artificial intelligence, AI for short, that enables systems to learn and improve from experience automatically without being explicitly programmed. Think of it as teaching computers to recognize patterns and make decisions based on data. But how does that work, you ask? Well, it's all about algorithms. Machine learning algorithms are designed to parse through data, learn from it, and then apply that knowledge to make decisions or predictions. One of the most popular libraries used in machine learning is called SCIKIT, a powerful and user-friendly tool that has made machine learning accessible to many. This library provides simple yet efficient tools for data analysis and is built on top of other established Python libraries like NumPy, SciPy, and Matplotlib. As we proceed, you'll see practical examples using this library that will help illuminate its functionality. Let's dive in. Now that you have Python and scikit-learn installed, let's explore how to leverage scikit-learn for machine learning. First, open your terminal or command prompt and run the command to install the library. This will ensure you have the latest version along with all its dependencies. If you're working in Jupyter Notebook, simply add an exclamation mark before the command to install it directly within your notebook environment. Once you've installed scikit-learn, you're all set to start your journey into the world of machine learning. Next, we need to address a common concern when working in that Jupyter Notebook environment. Here, you might want to execute the installation command right inside your notebook. By using the exclamation mark before the installation command, you can seamlessly install any required packages right where you're coding. This approach makes your workflow more efficient, allowing you to stay within the notebook as you progress through your machine learning tasks. With everything set up, you're now ready to dive into practical applications and begin building your machine learning models. Now, let's dive into how we can get started with loading the iris dataset and preparing our features for analysis. First up, we need to import a few necessary libraries. NumPy, which is great for numerical operations, and Pandas, perfect for data manipulation. Then there's scikit-learn, our go-to for accessing datasets and modeling tools. We'll use the load_iris function to fetch the iris dataset, which features various characteristics, including sepal length, sepal width, petal length, and petal width. Now let's assign these features to a variable called x, and the corresponding species labels go into a variable named y. It's like giving our data a good home. Next, we'll split this data set into training and testing sets using the train-test-split function. This way, we can train our model on part of the data and keep a separate portion aside for testing its performance. Here we've specified that 20% of the data will be designated for testing. And to ensure our data set is split consistently every time we run this code, we set the random state parameter. This controlled randomness is essential for getting those reproducible results that are so crucial for effective model evaluation. So let's make these numbers work for us. Now, let's dive into implementing the random forest classifier to train our model. We'll start by creating an instance of the random forest classifier, and for this, we'll specify the n-estimators parameter to be 100. This parameter indicates that we want to build 100 decision trees in our forest. Typically, this enhances our model's accuracy, but keep in mind, it does require more computational resources. Next, we'll fit the model to our training data by using the fit method and passing in xtrain and ytrain. This step is where our model learns the patterns from the training dataset. After that, we're ready to make predictions. By calling the predict method on our classifier object and passing the test data, xtest, we'll generate predictions for the iris species. Finally, we need to evaluate our model's performance. We can do this using the accuracy score function, which compares the true species labels from y-test with our predicted labels and then calculates the accuracy. The printed accuracy score will give us a sense of how well our model is performing, ranging from 0 to 1, where a score closer to 1 indicates better model performance. Now, let's dive into implementing hyperparameter tuning to optimize our random forest classifier. First up, we need to import the grid search CV from the sklearn.model-selection module. This tool is powerful for automating the hyperparameter tuning process, allowing us to use cross-validation to really refine our model. Next, we define a parameter grid. Think of it as a dictionary that specifies the values for n_estimates and max depth that we want to test. Now, just to clarify, n_estimates refers to the number of trees in our forest, while max depth sets the maximum depth each tree can reach. Here, we're testing 3 different values for n_estimators, 50, 100, and 200, along with 4 potential values for max depth, none, which means no limit, and then 10, 20, and 30. Moving on, we create an instance of grid search CV, passing in our classifier and the parameter grid, and we set the number of cross-validation folds to CV equals 5. This setup allows grid search CV to train and evaluate models based on those various combinations of parameter values. Then we call the fit method on our grid search instance and provide our training data to kick off that tuning process. Once that's completed, we can easily access the best combination of parameters found during this process by checking gridsearch.bestparams, which helps us fine-tune our model without needing to make extensive manual adjustments. Next, we're going to write some code that helps us enhance our dataset a bit more. Instead of just using the original measurements of petal length and petal width, let's calculate the ratio of these 2 dimensions. This petal ratio could really uncover a significant relationship between petal length and width, potentially improving how accurately our model predicts outcomes. So, to get started, we'll tap into our existing feature columns in the dataset. Specifically, we'll reference x4,2 for petal length and x4,3 for petal width. By dividing these 2 columns, we'll create a new array that we'll call petal ratio. Now, we want to incorporate this new feature back into our original dataset x. For that, we can use the np.columnStack function, which nicely stacks our existing data with this newly calculated petal ratio, resulting in a fresh array that we'll denote as xnew. With xnew, we now have this additional column for petal ratio, allowing us to resplit our dataset and retrain our classifier. This integration of feature engineering can really beef up our model, possibly leading to better performance when we're making predictions. Let's see how we can implement linear regression using the Boston housing dataset, which is a popular dataset for regression tasks. First, we need to import the necessary libraries to load our dataset and create our regression model. By calling the load Boston function, we can extract the features, also known as independent variables, and the target variable, which in this case is house prices. These are then stored in x_Boston and y_Boston, respectively. Next, we create an instance of the linear regression model. This involves initializing the model with the variable LR, representing our linear regression model. Once we have our model all set, we fit it to our data by calling the fit method with x_Boston and y_Boston. This step is crucial. It trains our model to learn that important relationship between the input features and the target values. Following the model training, we're going to make predictions using our input data, and for that, we'll use the predict method. These predictions are really key. They help us understand how well our model performs when estimating house prices based on the features we've provided. Finally, to evaluate our predictions, we calculate the mean squared error, MSE. This quantifies the average squared difference between our predicted values and the actual values, allowing us to assess how accurately our model is performing. Next, let's visualize the distribution of our target variable, which in this case are the house prices from the Boston housing dataset. Understanding this distribution is really important because it gives us valuable insights into our data, helping us determine the best strategies for modeling. To do this, we'll be leveraging the Seaborn library, a fantastic tool for creating visually appealing statistical graphics based on matplotlib. We'll kick things off by calling sns.histplot, which will generate a histogram for the house prices stored in y_Boston. The bins equals 30 parameter specifies how many bins we should use to group our data, giving us a clearer view of the distribution. And to add a bit more detail to our visualization, we can set KDE equals true. This overlays a smooth kernel density estimate, which approximates the probability density of our variable. Lastly, we'll label our x-axis as house prices and give the plot a title, Distribution of House Prices, so it's very clear what we're looking at. Then we just call plt.show to render the plot. By examining this visualization, you can easily get a sense of whether the house prices are normally distributed or if they're skewed in some way. This information is crucial as it can significantly influence your future steps in machine learning modeling. As we unwind our journey through machine learning, remember that this field is a vast ocean of possibilities. You can definitely explore deeper topics like neural networks, support vector machines, and those more advanced ensemble methods, like XGBoost. Resources are abundant, trust me on this, and continuous practice, that's key to mastering these concepts. And hey, don't hesitate to participate in online competitions like those on Kaggle. It's a fantastic platform where you can apply your skills to real-world problems while really learning from the community. Now, here's the thing. Machine learning isn't just about fitting models and chasing after good accuracy. It's truly about problem-solving and making data-driven decisions. Whether you're diving into finance, healthcare, or tech, the skills you develop here can have profound impacts on industries and, on day-to-day lives too. Thoughtful pause. Machine learning, with the help of libraries like scikit-learn, creates this dynamic toolkit for automating decisions and making predictions based on data. Your journey into this exciting field has merely begun, and the best way to learn is to experiment and continually engage with new challenges. So, dive in, start building those models, and who knows what incredible insights you might uncover. It's going to be a fun ride. Machine learning is an incredible field that's reshaping how we process and analyze information. In this session, we're going to dive into the various key algorithms used in machine learning. So far, we've learned that machine learning is a crucial aspect of artificial intelligence, allowing systems to learn from data without needing explicit programming. We've explored the basics of setting up a machine learning environment, focusing particularly on the scikit-learn library, and tackled classification and regression problems with examples like the Iris and Boston housing datasets. Additionally, we've discussed the importance of hyperparameter tuning and feature engineering in enhancing model performance. Now, let's not forget the significance of exploratory data analysis, which can uncover insights in our data and drive our understanding. And remember, continual learning through practical application and engaging with the community is key to mastering this field. Now, let's shift our attention to understanding the fundamental algorithms that power our machine learning models. All right, here we go. Now, let's dive into implementing the necessary libraries and preparing our dataset for linear regression. We begin by importing some essential libraries. First up, we have NumPy for our numerical operations, Pandas for data manipulation, and Matplotlib for visualization. Oh, and let's not forget, we also need to import train test split from scikit-learn to help us split our data set effectively, and linear regression to create our regression model. All right, next, we'll define a sample dataset that captures the relationship between housing area and prices. We can create a simple dictionary using area and price as our keys, and then easily convert this dictionary into a Pandas data frame. This way, area will serve as our predictor variable, while price is our target variable. Now that we've got our data prepared, let's move on to splitting it into training and testing sets using train test split. This, of course, allows us to assess our model's effectiveness on unseen data. We'll set our test size to 20% to ensure a representative evaluation, making sure we've covered our bases. Following that, we'll create our linear regression model using linearregression.com and fit it to the training data. This step is crucial as it teaches the model the relationship between our predictor and target. Once our model is trained, we'll make some predictions on the test dataset to see just how well it performs. Next, we're going to dive into implementing logistic regression, which is, a powerful classification algorithm that's really handy. To kick things off, we'll need to import some essential libraries. Specifically, we'll grab scikit-learn's logistic regression class and the make classification function. This is what we'll use to generate a synthetic dataset. Now, this dataset will feature two, yes, just two, features and will be divided into two classes. It's all about simulating a binary classification scenario, which is quite interesting. So, let's jump in and generate that synthetic dataset using make classification. We'll need to set parameters like the number of samples, features, and informative variables. This is key to creating a meaningful dataset for our model. Now that we have our data all set up, it's time to split it into training and testing sets. We're going to use train test split for this, making sure to reserve 20% of the data for testing our model later on. Now, what's next? Let's create and fit our logistic regression model to the training data, which involves initializing the model and then applying it using the fit method. This is where the magic happens. The model learns from the training inputs and their corresponding labels. But we're not done yet. After fitting the model, it's super important to evaluate its performance. So we'll check the model's accuracy on that test set using the score method, which gives us a value between 0 and 1. Pretty neat, right? Lastly, we want to visualize the decision boundary. This will give us some insight into how the model distinguishes between the two classes based on those learned features. Now, let's implement a simple decision tree model using the Iris dataset. First, we need to import the necessary libraries, specifically from scikit-learn, which is essential for working with our dataset and creating our decision tree classifier. Let's load the iris dataset. This dataset, by the way, consists of features from different iris flower species. We will separate this into features, which we'll call X, and target labels, which we'll call Y. Next up, we'll split our dataset into training and testing sets, which is vital for evaluating our model's performance. And we'll do this by using the train-test-split function. Here, we're going to allocate 20% of the data for testing. This provides an opportunity to train our model and then validate its accuracy on unseen data. Now, let's create an instance of the decision tree classifier and fit it to our training data, allowing the model to learn the necessary patterns for classifying the species based on the provided features. Once we've trained the model, we can visualize the decision tree using the plot tree function. This function gives us a clear graphical interpretation of the decision-making process within the model. It illustrates how data is split at each node based on feature values, which honestly makes it much easier to grasp how our model is arriving at its decisions. Now, let's implement a support vector machine, or SVM model, using a dataset from scikit-learn. First, we start by importing the necessary libraries. Then, we create a synthetic dataset that has a nonlinear shape. It's often affectionately called moons. This particular setup really helps illustrate how SVM can work with those complex boundaries. After generating our dataset, we split it into training and testing sets. This step is crucial. It ensures that we can evaluate just how well our model is performing. Next, we'll create our SVM model using the radial basis function, or RBF, kernel. This kernel is particularly effective for handling nonlinear relationships within our data. So, we fit the model to the training data. This allows the SVM to learn the optimal hyperplane. You know, the one that effectively separates our different classes. Once our model is trained, we evaluate its performance by calculating the accuracy on the test set. This metric is super important. It tells us how well our model is predicting compared to the actual class labels. Now, to really visualize how our SVM model distinguishes between those classes, we'll create a function to plot the decision boundary. This function will generate a grid of points stretching across the feature space and predict class labels for these points based on how our model was trained. By plotting the decision boundary alongside the actual data points, we can clearly see how effectively the SVM captures the underlying structure of our dataset. Now, let's dive into implementing a random forest classifier using the iris dataset to really explore the power of ensemble methods. First up, we need to import the necessary random forest classifier from scikit-learn, and yes, we'll load the iris dataset again. Think of this as our training and testing ground for the model. Next, we'll split the data into training and testing sets, making sure to allocate 20% for testing. This helps us adequately evaluate our model's performance, which is super important. Now, we create an instance of the random forest classifier where we can specify the number of decision trees to include in our ensemble using the parameter n-estimators. This is crucial, you see. Having more trees tends to give us better accuracy. Plus, it acts as a safeguard against overfitting. Once we fit our model to the training data, we evaluate its effectiveness by calculating its accuracy on the test set. A clear output showing the model's accuracy provides us insight into how well the random forest has learned to classify the iris species. Finally, let's retrieve the feature importances, allowing us to understand which features of the dataset significantly influence the model's decision-making. By ranking these features based on their importance, we can gather valuable insights for future modeling tasks and, who knows, maybe enhance feature selection in our analyses. To wrap this up, we've covered a variety of key algorithms in machine learning, including linear regression, logistic regression, decision trees, support vector machines, and random forests. Each of these algorithms is well suited for its specific tasks, and understanding their implementations and applications significantly aids in model selection for your particular problem. As you advance in your journey with machine learning, it's essential to experiment with these algorithms and truly understand the mechanics behind them. Remember, practical application is the best teacher. Whether you're tweaking hyperparameters, trying out new datasets, or optimizing your models based on evaluation metrics, that hands-on experience will really solidify your knowledge. Machine learning is an exciting field with endless possibilities, and I encourage everyone to dive deep, explore, and most importantly, enjoy the learning process. Thank you for joining this exploration of key algorithms in machine learning, and I look forward to seeing what you all create. Machine learning has numerous applications and is continually evolving, transforming the way we interact with technology across various sectors. In today's lesson, we'll dive into the fascinating applications of machine learning in different domains, explore its future directions, and analyze how these trends will shape our lives. So far, we've learned that machine learning is a crucial aspect of artificial intelligence, allowing systems to learn from data without needing explicit programming. We've covered essential algorithms, including linear regression, logistic regression, decision trees, support vector machines, and ensemble methods like random forests. Now, we're going to venture into real-world applications and what's on the horizon in this ever-evolving landscape of machine learning. You'll see just how much these technologies are influencing our daily lives and the exciting future that lies ahead. Now, let's dive into implementing a convolutional neural network, or CNN, designed specifically for image classification using TensorFlow and Keras. First up, we need to import the essential libraries that will help us build and train our model effectively. So, the CNN architecture kicks off with a sequential model. This enables us to stack layers in a simple, linear way. We start with a convolutional layer that uses 32 filters and a kernel size of 3 by 3. Here, we also apply the ReLU activation function, which introduces nonlinearities that help the model learn those complex patterns hidden in our X-ray images. After we've got our first convolutional layer in place, we throw in a max pooling layer to downsample the feature maps. This step reduces dimensionality and also lightens the load on our computational resources. Next, we add another convolutional layer with 64 filters, followed by another round of max pooling. This further hones our feature extraction process. Once we're satisfied with our convolutional layers, we flatten the output to convert that 2D matrix into a 1D vector, which we then feed into our fully connected layers. The first dense layer also applies ReLU activation, and then we finish off with an output layer that employs the sigmoid activation function for binary classification. This is crucial for distinguishing between healthy lungs and those that are affected by pneumonia. Finally, we compile the model using the Atom optimizer along with a binary cross-entropy loss function, and we set accuracy as our performance metric. The model is trained on our dataset across a specified number of epochs, allowing it to learn the patterns associated with each class by minimizing the loss during that training process. Now, let's see how we can implement a logistic regression model for credit scoring using historical borrower data. First, we need to import the necessary libraries. We'll use pandas for data manipulation, train test split to split our dataset into training and testing subsets, logistic regression for building the model, and accuracy score so we can evaluate how well our model performs. Next, let's load our dataset, which contains borrower information along with their default status, into a data frame. In preparation for modeling, we'll separate the features, the independent variables used to evaluate creditworthiness, from the target variable, which indicates whether a borrower defaulted on a loan. Using train-test split, we'll divide our data into training and testing sets, training the model on one portion and evaluating it on the other, unseen part. Now, let's get to the exciting part, implementing the logistic regression model. We start by creating an instance of the logistic regression class and fitting it to our training data. After the model is trained, we'll make predictions on the test set. Finally, we'll calculate and print the accuracy of our model, giving us insight into how well it predicts loan defaults based on the input features, and demonstrating a significant application of machine learning in finance. Next, we will implement a collaborative filtering model using the surprise library to demonstrate how machine learning can enhance recommendation systems in retail and e-commerce. First, let's load a dataset. Specifically, we're using the Movie Lens dataset, which is, kind of a standard choice for testing out recommendation algorithms. To access this dataset, we'll use the dataset.load-built-in ml-100k function, which makes it super easy, and it's got 100,000 movie ratings for us to work with. After loading the data, we split it into a training set and a test set using train-test split. Here, we allocate 80% for training and 20% for testing. This way, we can later evaluate how well our model performs. Now, we'll implement the singular value decomposition, or SVD, algorithm. This is a popular method for collaborative filtering. We simply call SVD, and then fit it to our training set using model.fit_trainset, which, allows the model to learn from all those user ratings. Once it's trained, we can generate predictions for the test set using model.testset. Slight pause. Finally, to measure how accurately our recommendations are, we use the root mean square error, or RMSE. We compute this with accuracy.rmse predictions, and this really gives us a clear picture of how well our model is predicting user preferences. Now, let's dive into implementing a basic reinforcement learning model to navigate a maze. We'll kick things off by creating a maze class. This class will initialize the maze with a specified size, pretty straightforward, and we'll set up a simple representation using a grid of zeros. Zeros indicate those empty pathways, right? The maze class will also include a step method, which is going to determine how our agent navigates through this maze, though at this point, the actual movement logic is yet to be defined. Now, next up, we'll introduce the Q-Learning Agent class. This is where the magic happens. It embodies the principles of Q-learning, a popular reinforcement learning algorithm. This agent will initialize a Q table. That's a crucial component, let me tell you, because it'll store and update the values representing expected future rewards for each action that can be taken from different states in the maze. We'll also set our learning parameters, like the learning rate and the discount factor, which really govern how the agent learns from its experiences and balances those immediate versus long-term rewards. Finally, we'll instantiate the maze and our Q-learning agent. This sets the stage for further development of our navigation logic and learning processes. It's a promising foundation. With this setup, our agent will be able to explore the maze using the principles of reinforcement learning, ultimately aiming to maximize its rewards as it finds optimized paths. Now, let's take a moment to explore how we can implement a smart home device that automatically adjusts lighting based on user behavior. We're defining a class named Smart Home Device, which initializes a lighting schedule with 24 entries, one for each hour of the day. We're using NumPy here because it makes handling array operations super convenient. Next up, we have a method called adjustLighting, which takes two parameters, hour and brightness. This method updates our lighting schedule by setting the brightness level for the specified hour. Once that's done, it prints a message confirming the change, so you know exactly when and how the lighting is adjusting. The cool part? This device can learn from user patterns over time, so it can autonomously decide on the optimal lighting levels without needing constant communication with a central server. This really shows off the potential of integrating machine learning into IoT devices, enhancing user experience while streamlining daily routines in smart homes. As we move forward, we can dive deeper into how machine learning algorithms can elevate this concept even more, making these devices even smarter and more responsive. Now, let's dive into implementing LIME, a really cool technique for explaining how our machine learning model makes its predictions. First up, we're going to import the LIME Tabular Explainer class from the lime.limetabular module. This class is specifically designed for tabular data and helps us figure out how our model interacts with each feature. So, we'll start by initializing our explainer. Just pass in the training data along with the feature names and class names that represent our target variable. Next, we'll want to make our continuous features a bit easier to understand, so we specify that we want to discretize them. Now, with our explainer all set up, we need to choose an instance from our test dataset that we wish to explain, denoted by the index I. This index points to a specific observation for which we'll analyze the prediction. Once we've got that, we'll call the explainInstance method. Just pass in the feature values of our selected instance along with the model's prediction probabilities. This method gives us an explanation object that lays out how each feature contributes to the prediction our model made. Finally, we can visualize these results right within a Jupyter notebook. Just use the Show in Notebook method and voila! You'll get an insightful overview of the model's decision-making process, which is super helpful for understanding its predictions better. In summary, the applications of machine learning are incredibly diverse, impacting various fields. Think healthcare, finance, retail, and even autonomous systems, among others. You see, machine learning isn't just about improving processes and efficiencies, it also enriches the user experience through personalized services and real-time decision-making. Now, as we look ahead, the evolution of machine learning is going to be driven by advancements in edge computing, explainable AI, and its integration into our everyday devices. Ultimately, adapting to these changes and harnessing the power of machine learning is crucial for both businesses and individuals. The future holds immense promise, and if we explore and understand these technologies judiciously, we can pave the way for innovative solutions and further advancements. As we wrap up this segment on the applications and future directions of machine learning, I really encourage you to stay curious and engaged in this ever-evolving field. The journey is just beginning, and the learning never stops. Thank you for joining me, and I look forward to our next session together. From the perspective of data handling, there are several essential techniques that serve as the foundation for effective data management and analysis. Understanding these techniques will empower us to work with data more efficiently and derive valuable insights, which is super exciting. Today, we'll explore data handling techniques in detail. Yes, we'll cover how to pre-process data, manage datasets, and utilize powerful libraries like NumPy and Pandas to perform these tasks. So far, we've learned that machine learning is a transformative force across various industries. We've touched on its applications, right? Now, let's dive into the nuts and bolts of specific data handling techniques that are absolutely vital for preparing data in your machine learning workflows. Now, let's implement a simple yet effective function to fetch data from a web API using Python. We begin by importing the requests library, which provides handy methods for enabling HTTP requests. In the fetchData function, we accept a URL as a parameter and use the requests.get method to send a GET request to that URL. This method returns a response object containing crucial information about the request, including the status code. Next, we check if the request was successful by evaluating if the status code equals 200, which indicates everything went smoothly. If it was successful, we can move ahead and return the data in JSON format by calling response.json. This is super important for data analysis since JSON is a widely used format that's easy to manipulate in Python. However, if the request fails, we raise an exception with a relevant error message to ensure any issues are addressed promptly. Pretty neat, right? To demonstrate how this function works, we'll define a variable, URL, that stores the API endpoint we're interested in. Then we call our fetchData function, passing in that URL, and we store the returned data in a variable called data. Finally, we print out the data to visualize what we've retrieved. This whole approach allows us to dynamically gather data for our analysis in a super convenient way. Now that we have a data frame with missing values, let's see how we can tackle those gaps in our data. First off, we'll create a sample data frame using a dictionary that holds names, ages, and cities. This data frame has some missing entries, specifically an absent name and a missing age, which is perfect for demonstrating how to handle such situations. Next, we'll display the original data frame to visualize those missing values. It's always good to take a peek at what we're working with. To address the missing data in the age column, we're going to use the fill_l method. This nifty tool lets us replace any missing entries with the average age calculated from the existing values. By doing this, we're not just filling in blanks, but also ensuring that we keep a sensible value in our numeric columns, which helps maintain the robustness of our analysis. Now, for the name column, what we'll do is use a placeholder value, unknown, to fill in those gaps. This way, we keep the integrity of our dataset intact while prepping it for more advanced analysis. Finally, we'll display the modified data frame. And voila! The previously missing values have been successfully filled, allowing us to move forward with further data processing and analysis without losing any critical information. Now let's see how we can implement data type conversion to ensure our data frame contains the correct data types for each column. In this example, we're focusing on the age column, which may have been read as a string type. To address this, we'll use the asType function from Pandas. This neat little tool allows us to change the data type of a column. Specifically, we're going to convert the age column to an integer type, which is super important because it ensures we can perform mathematical operations on it in future analyses without running into issues. Now, after the conversion, it's essential to verify that these changes were applied correctly. We do this by displaying the data types of all columns in the data frame using the dTypes attribute. This step is crucial because having the proper data types not only prevents errors during calculations, but also significantly enhances performance during data analysis. Remember, if you treat numeric data as strings, you'll miss out on those powerful numerical computations and manipulations that are necessary for effective data handling. By ensuring our data frame is equipped with appropriate data types, we're really laying a solid foundation for the subsequent stages of our analysis. Now, let's implement the min-max scaling technique to normalize the age column in our data frame. First, we're going to begin by importing the min-max scaler from the sklearn.preprocessing module. This tool is specially designed to scale features by transforming them into a specified range, usually between 0 and 1. So, let's initialize the scaler by creating an instance of min-max scaler. Next, we'll fit the scaler to the age column in our data frame, and while we're at it, we'll apply the transformation. This step adjusts the scaling of each value based on the minimum and maximum values found in that column, ensuring the entire column is normalized to our chosen range. The transformed values will then be reassigned back into the data frame, emphasizing replacing the original age values. Finally, we'll print the modified data frame to see the changes. This scaling step is super important, especially for algorithms that measure distances, like k-nearest neighbors, because it guarantees that all features contribute equally to the analysis. Plus, it boosts the performance of our machine learning model. Next, we're going to write some code that adds a new column for income to our data frame. So imagine this. We create an income column that's filled in with specified income values, but just to keep it realistic, we'll include some missing entries too. Once we have that set up, we'll perform a really key operation, grouping the data by city to calculate the average income for each city. This is super easy with the group by method. It lets us specify exactly which column we want to group by, and then we follow it up with the mean function to compute those averages for the income column. Now, grouping data like this isn't just about summarizing it effectively. It also helps uncover patterns and insights that might be, well, kind of hidden when you're looking at raw data alone. Finally, let's wrap this up by using the print function to display our results. It'll show us the average income for each city in our dataset. This step really highlights the power of aggregation functions in Pandas and emphasizes how these techniques are crucial for analyzing and interpreting large datasets. Now, let's see how we can implement merging datasets using the Pandas library. First, we create a second data frame called IncomeDF, which holds information about the names and incomes of individuals. By defining a dictionary with names and corresponding income values, we can easily transform this data into a data frame. Next, we utilize the powerful merge function from Pandas, which allows us to join two data frames on a common column, here the name column. The how outer parameter ensures that we retain all records from both data frames even if they don't have matching entries. This means that if a name appears in one data frame but not the other, the output will still include that entry, filling in any missing values with nans. Finally, we print the merged data frame, which gives us a cohesive view of the combined data. This operation highlights the importance of merging in data analysis, as it enables us to enrich our datasets and gain a more comprehensive understanding of the information at hand. Now, let's see how we can reshape our data frame to better organize the data for analysis. We'll utilize the pivot function, which allows us to transform the data frame into a wider format. Here's the cool part. Each unique name will become its own separate column, while city serves as the index. This setup effectively displays the age of each individual in relation to the city they belong to. By specifying index equals city, we ensure that each row corresponds to a specific city. The columns equals name argument generates columns for each person's name, and values equals age lets us fill the newly formed data frame with their ages. This way, visualizing how ages are distributed across different cities becomes really easy. So, once we execute this code, we'll print the pivoted data frame, which gives us a clear view of age distribution among individuals grouped by their respective cities. This reshaping technique not only streamlines the data, but also makes it much more accessible and manageable for our next steps in analysis. It's truly an essential step in data manipulation that can vastly improve our understanding of the dataset. Now, let's take a moment to visualize our income distribution using Matplotlib and Seaborn, two powerful libraries that can really help us create some informative graphs. So, first things first, we need to import both libraries. This is like setting up our toolbox for plotting. All right, now moving on, let's set the figure size, which is crucial for making our plot both visually appealing and easy to read. We do this by calling plt.figure, figure size, equals 10,6, where we specify the dimensions. 10 inches in width and 6 inches in height works nicely. Next, we're going to use the Seaborn function sns.histoplot to create a histogram of our income data. By specifying bins equals 10, we can divide our income data into 10 distinct intervals, which really helps visualize the distribution across those ranges. And we're also going to enable the kernel density estimate, or KDE, which adds a smooth curve over the histogram. This really gives us a clearer understanding of the distribution shape. Now, after we've plotted that, it's important, right, to label our axes and give the plot a title. This not only improves readability, but also provides crucial context for anyone looking at the graph. Finally, we execute plt.show to display our plot, allowing us to visualize our findings effectively. This entire approach emphasizes the crucial role that visualization plays in interpreting and presenting data insights. Now, let's implement the following crucial steps for saving and loading our processed data. To begin, we can easily save our cleaned and transformed data frame into a CSV file format with just one command. By using df.toCSV, processeddata.csv, index equals false, we're instructing Python to take our current data frame, df, and save it as a file called processeddata.csv without including the index column. This is particularly useful because it keeps the file clean and focused on the actual data. Now, let's see how we can load this data back into our environment when we need to work with it again. The command loadeddf equals pd.readcsv, processeddata.csv, allows us to read the CSV file we just created back into a new data frame, loadeddf. Brief pause. Now we can manipulate and analyze our previously processed data without having to repeat all those pre-processing steps. This whole process of saving and loading data is essential, as it not only preserves our work, but also enables efficient data handling in future analyses.
Advanced model evaluation is crucial for understanding how well a model is performing. In machine learning, the right evaluation metrics can provide deep insights into model accuracy, generalization, and practical performance. So far, we learned that effective data management and analysis relies on essential techniques such as data collection, preprocessing, and utilizing libraries like pandas and NumPy. We explored key processes like handling missing values, normalizing data, merging datasets, and reshaping data for better usability. Additionally, we discussed the importance of data visualization and saving loading datasets to facilitate future analysis. With these foundational skills, you are well prepared to tackle various data challenges in your machine learning workflows. Now we will cover advanced model evaluation methods that will help you to gauge the performance of your models more comprehensively. To get started, it's essential to understand that evaluating machine learning models effectively goes beyond simply checking accuracy. While accuracy is a valuable metric, it can be deceiving, especially in cases of imbalanced datasets. Thus, it's crucial to employ multiple evaluation techniques that provide different perspectives on model performance. Now let's see how we can implement the confusion matrix using Python's scikit-learn library. We begin by importing the necessary libraries, specifically confusion matrix from sklearn, metrics, and numpy for handling arrays. First, we define our true labels, whiteTrue, and the predicted labels, whitered. These arrays represent the actual outcomes and the predictions made by our model, respectively. For our illustration, we use a binary classification scenario, where each label can either be a 1 positive or a 0 negative. Next, we generate the confusion matrix by calling the confusion matrix function with our true and predicted labels as arguments. This function computes the matrix that summarizes the classification results, showing how many true positives, correctly predicted positives, false negatives, missed positives, false positives, incorrectly predicted positives, and true negatives, correctly predicted negatives, our model produced. Finally, we print the confusion matrix to visualize these performance metrics, allowing us to gauge how effectively our classification model is performing and where it might be making errors. Understanding this matrix is crucial for improving the model's predictive capabilities. Now let's see how we can implement precision and recall calculations using scikit-learn. We begin by importing the necessary functions, precision score and recall score, from the SCIKIT metrics module. These functions will allow us to evaluate our classification model's performance based on the true labels and predicted labels. Next, we calculate precision and recall by passing in two arguments: whitetrue, which represents the actual binary labels, and whitered, which contains the predicted labels generated by our model. Precision gives us insight into the accuracy of our positive predictions by measuring the ratio of true positives to the total number of predicted positives, thus helping us understand how many of those predicted positive cases were actually correct. On the other hand, recall tells us how effective our model is at identifying true positive cases by comparing the number of true positives to the total actual positives. Finally, we print the precision and recall values to the output. This step is critical, as it enables us to assess our model's reliability and effectiveness, especially in contexts where correctly identifying positive cases is crucial, such as in medical diagnoses or fraud detection. Now let's see how we can implement the calculation of the F1 score using the scikit-learn library. First, we start by importing the F1 score function from the SCIKIT metrics module. This function is essential for evaluating the balance between precision and recall in our classification model. Next, you'll notice that we have two arrays, whitetrue and whitered. The whitetrue array contains the actual labels of the data, while the whitered array holds the predicted labels generated by our model. With these two sets of labels, we can compute the F1 score, which gives us a single metric encompassing both precision and recall. To calculate it, we call F1 score and pass in whitetrue and whitered as arguments. The result of this function will be stored in the variable F1, which we then print to see the calculated F1 score. This score provides valuable insight into how well our model is distinguishing between the positive and negative classes, especially in scenarios with imbalanced datasets. Now let's see how we can implement two essential metrics for evaluating regression models: mean absolute error MAE and mean squared error MSE, along with the R2 score. First, we begin by importing the necessary functions from the SCIKIT metrics module, which equips us with the tools needed for our calculations. Next, we define two NumPy arrays, y-actual and y-predicted, that hold the true values and the values predicted by our model respectively. This setup allows us to compare how closely our model's predictions align with the actual outcomes. Once the data is structured, we proceed to calculate the MAE, which provides a straightforward average of the absolute differences between the actual and predicted values, thus giving us an intuitive measure of prediction accuracy. We also compute the MSE, which squares the differences to emphasize larger errors, making it particularly useful for identifying significant discrepancies in predictions. Following that, we will assess our model's strength with the R2 score, a key metric that quantifies the proportion of variance explained by the independent variables, where scores closer to 1 denote our model performs well. The results of these calculations will help us gauge the effectiveness of our regression model comprehensively. Now let's see how we can implement cross-validation to assess the performance of our model. First, we import the necessary functions from the scikit-learn library, specifically cross-val score for performing cross-validation and random forest classifier, which is our chosen model for this demonstration. Next, we create an instance of the random forest classifier, which is a popular ensemble learning method that builds multiple decision trees and combines their outputs for improved accuracy. Once the model is ready, we proceed to perform 5-fold cross-validation by calling cross-val score with our model feature dataset X target variable Y and the parameter CV equals 5 that specifies the number of folds. This function will split the dataset into 5 parts, training the model on 4 of these and validating it on the remaining one, repeating this process to ensure each fold serves as a validation set once. The output is an array of scores corresponding to each fold's performance. Finally, we print out the individual cross-validation scores, as well as the mean score, which provides a comprehensive insight into how well our model is likely to perform on unseen data. Now let's see how we can implement stratified sampling for cross-validation in scikit-learn. We begin by importing the stratified k-fold class from the SCIKIT model selection module. This class is specifically designed to handle cases where the target variable is imbalanced, ensuring that the same proportion of classes is present in both the training and testing subsets. Next, we'll define our feature set X and our target variable Y, which you would typically obtain from your dataset. By instantiating the stratified k-fold object with a specified number of splits, in this case 5, we can generate stratified folds. The split method is then used, which takes x and y as input to yield the indices for the training and testing sets. Inside the loop, we create xtrain and xtest by indexing x with the provided training and test indices, respectively. Similarly, we set up ytrain and ytest for the target variable. Once the data is split, you can proceed to fit your model with the training data, ensuring that each fold gives a balanced representation of the classes, leading to more reliable evaluation results. Now let's implement the ROC curve to evaluate the model's performance. First, we start by obtaining the predicted probabilities for the positive class using the predict-proba method of our trained model. This method gives us the likelihood of each instance belonging to the positive class, and we specifically extract the second column, which corresponds to these probabilities. Next, we calculate the false positive rates, FPR, and true positive rates, TPR, across various thresholds using the ROC curve function. This function provides an array of FPR and TPR values, along with the thresholds used to generate them. These rates are crucial for understanding how sensitive or specific our model is at different classification thresholds. After obtaining the FPR and TPR, we can summarize the model's overall performance by calculating the area under the curve, AUC, with the awk function. The AUC quantifies the model's capability to distinguish between the two classes, with values closer to 1 indicating better performance. Finally, we proceed to visualize the ROC curve using matplotlib. By plotting the TPR against the FPR, we create a graphical representation of the trade-offs between true and false positive rates, allowing us to assess the model's performance visually. Also, we add a diagonal line to represent random performance for better context. In conclusion, advanced model evaluation methods provide the necessary insights for fine-tuning our machine learning models, guiding decisions based on comprehensive metrics. We covered essential techniques such as confusion matrices that reveal the inner workings of classification models, precision and recall to address model reliability, F1 scores to balance performance measures, regression metrics for evaluating continuous outputs, cross-validation techniques for achieving generalization, stratified sampling for equitable data representation, and ROC curves for understanding classification trade-offs. Understanding these concepts and methods equips you with a robust toolkit necessary for building and evaluating machine learning models rigorously. It gets exciting, like leveling up in a video game. Each new skill enhances your ability to tackle real-world data problems effectively. Keep practicing, experimenting, and learning, and you'll become more adept at harnessing these techniques in your machine learning journey. Happy Interpretability is a significant aspect of machine learning that facilitates understanding complex models and their predictions. As we dive into this topic, we will explore the importance of interpretability, different approaches to make machine learning models more transparent, and the tools available to help us achieve that clarity. So far, we learned about advanced model evaluation techniques, emphasizing the importance of selecting the right metrics to gauge model performance effectively. We explored confusion matrices, precision, recall, and F1 scores for classification tasks, as well as key regression metrics like mean absolute error and R2 score. Additionally, we discussed cross-validation, stratified sampling, and ROC curves as essential methods to ensure model reliability and performance across various scenarios. Now we will talk about interpretability and transparency in machine learning, exploring why they matter and how to implement them effectively. To start, it's crucial to understand that interpretability in machine learning refers to our ability to explain and present the predictions made by a model in human understandable terms. Interpretability helps not only data scientists and engineers, but also stakeholders who rely on the models for decision-making. These decisions might involve approving loans, diagnosing medical conditions, or even determining the fairness of hiring practices. If a model operates in a black box manner, it can lead to mistrust and inconsistencies. Think about an audience asking why a model decided to reject a loan application. Without a clear answer, we could run into issues of accountability. Now let's implement a logistic regression model to predict loan approval based on income and credit score. First, we import necessary libraries, including pandas for data manipulation and scikit-learn for building the model. Next, we create a sample dataset containing income, credit scores, and loan approval outcomes, represented as binary values, 1 for approved and 0 for not approved. We then convert the raw data into a pandas data frame for easier handling and split the dataset into features, income and credit score, and the target variable, loan approval. This separation allows us to effectively train the model on input data while predicting the outcomes. Using the train test split function, we divide the data into training and test sets, which helps evaluate the model's performance on unseen data. Next, we fit the logistic regression model with the training data. Once the model is trained, we extract the coefficients, which provide insight into how each feature influences the likelihood of loan approval. Specifically, a positive coefficient for income indicates that an increase in income enhances the probability of being approved for a loan, which underscores the model's interpretability. Finally, we print the coefficients to summarize the relationship between the input features and the predicted outcomes. Now let's implement SHAP to explain predictions made by a random forest classifier. We begin by importing the necessary libraries for our task, including SHAP and the random forest classifier from scikit-learn. Next, we set up our sample dataset, which comprises 2 features and a corresponding target variable, allowing the model to learn patterns related to classifications. After creating a pandas data frame to store our data, we separate the features, feature 1 and feature 2, from the target variable target. This sets the stage for model training. We then instantiate a random forest model and fit it to our training data, allowing it to learn from the patterns within the features to make predictions. Now we move on to explain the model's predictions using SHAP. We first create a SHAP explainer specifically designed for tree-based models by calling SHAP tree explainer with our trained random forest model. This captures the model's expected values and SHAP values for each instance. Finally, we visualize the SHAP values for the first instance using a force plot, which helps us understand how each feature influenced the model's prediction, effectively demystifying the decision-making process behind the model. Now let's implement Lime to enhance the interpretability of our random forest model. First, we import the necessary libraries, specifically Lime's tabular explainer, which is suited for handling tabular data. We create an instance of Lime tabular explainer, where we provide the training data in the form of a NumPy array, specify the mode as classification, and include the feature and class names. This setup enables Lime to understand the structure of our data and class categories for interpretation. Next, we focus on explaining an individual prediction from our model. By using the explain instance method, we pass in the feature values of the instance we want to analyze along with the model's probability predictions. This method produces an explanation that approximates the model's behavior in the vicinity of the selected instance. To visualize the insights generated by Lime, we utilize the show in notebook method. This allows us to see a detailed breakdown of how each feature influenced the decision made by our random forest model, highlighting the complexity behind its predictions. Through this process, Lime offers clarity and transparency in interpreting model outputs. Now let's implement a practical example using AIF 360 to assess fairness in a machine learning model. We start by importing necessary classes from the AIF 360 library and creating a sample dataset that includes features for 2 types of gender bias alongside loan approval status. This dataset will serve to evaluate our model's predictions across different demographic groups. Next, we construct a data frame using the dataset and convert it into a binary label dataset, which is specifically designed for binary classification tasks and allows us to specify the label names and protected attributes. This step is crucial in framing our analysis of fairness against demographic factors. Following the dataset setup, we use the binary label dataset metric to calculate fairness metrics, focusing on the disparity between privileged and unprivileged groups, here defined by gender. By calling the method for calculating disparate impact, we can uncover whether the model exhibits a preference for one gender over another when approving loans. Lastly, we print the calculated disparate impact to observe any biases that might exist in the model's predictions, ensuring we remain accountable to ethical standards in machine learning. As we consider interpretability, we must also recognize the trade-off we sometimes face between performance and interpretability. That is, a more interpretable model might not always yield the highest accuracy compared to more complex models. Therefore, it's essential to set clear objectives for model performance based on the specific use case. In certain scenarios, such as medical diagnostics or decision support systems, accuracy might be paramount, so using complex models with interpretability solutions, like SHAP or Lime, becomes necessary. However, in applications like loan approvals, where understanding the decision process is vital for customer trust, simpler models with good interpretability might outperform complex ones, even if they are slightly less accurate. In practice, you can often start with a simpler model, assess its interpretability and performance, and then iterate by introducing complexity as needed, always keeping interpretability in mind. As we draw to an end, remember that interpretability is more than just a nice-to-have feature in machine learning models. It is a critical requirement that enhances trust and accountability. By choosing suitable models, leveraging interpretability techniques such as SHAP and LIME, and actively auditing for fairness, we can build trustworthy systems that promote transparency in decision-making. The future of machine learning hinges on our ability to make these intelligent systems understandable, so we can ensure they are used responsibly and ethically. So that's it for today. We've covered how interpretability intersects with transparency in machine learning models by exploring various techniques and best practices. Remember, when we make our models explainable, we empower others to trust and utilize these models effectively. Keep experimenting with different methods and continue to strive for clarity in your machine learning projects. Until next time, happy. Feature engineering is a crucial process that greatly impacts model performance. It involves transforming raw data into meaningful features that better represent the underlying problem to the predictive models. In this video, we're diving deep into feature engineering techniques, which are important for enhancing the performance of machine learning models. So far, we've learned about the importance of interpretability in machine learning, which helps explain model predictions to stakeholders. We've examined advanced evaluation techniques for model performance, applying metrics like confusion matrices and cross-validation. We explored simpler models like linear regression for clarity, and introduced tools such as SHAP and LIME for explaining complex models. Lastly, we highlighted the importance of fairness in machine learning, emphasizing that transparent models must also be audited for bias. Now, we will cover various feature engineering techniques that can help improve your machine learning models. Now let's see how we can implement feature scaling using Python's scikit-learn library. We start by importing the necessary libraries, including min-max scaler and standard scaler from scikit-learn, as well as pandas for data manipulation. We'll create a simple dataset consisting of house sizes and prices. This dataset includes two features, house size SQFT and price. Next, we apply min-max scaling, which transforms our features into a specified range, typically 0, 1. By initializing a min-max scaler instance, we fit and transform the data, assigning the scaled values to new columns in our data frame. This allows us to easily compare the results of our feature scaling. Following that, we implement standard scaling using a standard scaler. This technique standardizes the features by centering the data around the mean with a standard deviation of 1. Again, we fit and transform the original features and store the results in new columns. Finally, we print the data frame that now includes both the scaled features, enabling us to see how the scaling has adjusted our data for better comparison across different ranges. Next, we will implement dummy variable creation to convert categorical data into a numerical format suitable for machine learning algorithms. To begin, we create a sample dataset with a categorical feature color, which has 3 possible values, red, blue, and green. We use a dictionary to structure our data and then convert it into a pandas data frame. Now let's see how we can achieve one-hot encoding through the PD getDummies function. This function takes our data frame and transforms the color column into separate binary columns for each category present, excluding one to avoid multicollinearity. This is facilitated by the drop first equals true argument. By doing so, the colors blue and green will be encoded as new columns named color blue and color green, with 1s and 0s representing the presence or absence of these categories respectively. Finally, we print the newly encoded data frame to visualize how our original categorical variable has been effectively transformed into a numerical format that machine learning models can utilize. This process is crucial for ensuring that our algorithms can interpret categorical data correctly and enhance their performance. Now let's see how we can implement recursive feature elimination, RFE, to select the most important features of the Boston housing dataset. First, we load the Boston dataset, which contains various attributes of houses and their corresponding prices. We convert the dataset into a pandas data frame for easier manipulation and store the target variable, which is the house prices, in a series. Next, we create an instance of the linear regression model, which will be used as our estimator in the RFE process. RFE works by recursively removing the least significant features, allowing us to focus only on the most informative ones. We configure our RFE instance to select the top 5 features by passing the model and the number of desired features. Once we fit the RFE model to our data, it ranks the features based on their importance. Finally, we print out the names of the top features identified by RFE. This step is crucial in our feature selection process, as it helps enhance the model's predictive power and reduces the risk of overfitting by eliminating less relevant features. Now let's see how we can implement principal component analysis, or PCA, to extract features from our dataset. We begin by importing the PCA class from the Sklern decomposition module. Then we instantiate a PCA object specifying n_components equals 2 to indicate that we want to reduce our data to 2 dimensions. This is crucial for preserving the essence of our dataset as we transform the potentially high-dimensional data into a more manageable form. Next, we call the fitTransform method on our PCA object, passing in our dataset x. This method computes the principal components and then projects the data into this new reduced dimension, returning the transformed data. Following that, we convert the resulting array into a pandas date frame to facilitate easier data manipulation and analysis. We name the new columns principal component 1 and principal component 2 to clearly identify them. Finally, we print out the data frame to visualize the transformed data. This process effectively captures the underlying structure of the original dataset while mitigating the risk of overfitting, demonstrating how PCA can improve the performance of our machine learning models. Now let's implement the following code to create interaction features between two existing features, size and location. First, we define a dictionary containing our example data, where size represents the property size in square feet and location indicates whether the property is located in an urban or suburban area. This data is then transformed into a data frame using pandas, which will enable us to manipulate and analyze the data more efficiently. Next, we create the interaction feature named sizeLocation. This feature combines the size and location variables to better capture the impact of their relationship on property desirability. Specifically, we multiply the size by a mapped value representing location, assigning a value of 1 for urban properties and 0.5 for suburban properties. This approach allows us to scale the impact of size based on the type of location effectively. Finally, we print the data frame to display our original features alongside the newly created interaction feature. By examining these results, we can see how the interaction between size and location produces a valuable new variable that can enhance our machine learning model's performance. In conclusion, feature engineering is an essential part of the machine learning pipeline. The techniques we've covered, feature scaling, dummy variable creation, feature selection, feature extraction, and interaction features, are powerful tools to enhance model performance. These techniques allow us to transform raw data into meaningful features, ultimately leading to more accurate and reliable predictions. Remember, the better the features, the better your model's performance. Thank you for joining me in this exploration of feature engineering techniques. Don't forget to practice these techniques with your datasets and create models that not only perform better, but also yield meaningful insights. Happy coding, and see you in the next. Model tuning involves adjusting various parameters to improve performance effectively. In the world of machine learning, this is a vital process as it allows your models to reach their full potential by optimizing their accuracy and predictive capability. So far, we learned about the significance of feature engineering in enhancing machine learning model performance by transforming raw data into meaningful features. We explored techniques such as feature scaling, dummy variable creation, feature selection, and feature extraction, which are crucial for optimizing models. We also discussed the creation of interaction features to gain deeper insights from our data. These methods collectively aim to improve model accuracy and reliability in predictions. Now, we will talk about model evaluation and the various tuning strategies to ensure our models perform at their best. Now let's implement the following code to compute accuracy using scikit-learn. We begin by importing necessary libraries, including train-test-split for splitting our dataset into training and testing sets, random forest classifier for our machine learning model, and accuracy score to evaluate performance. Next, we define some sample data, where X represents the features and Y contains the corresponding target variable. We then split the dataset into training and testing sets using a 50% test size to ensure we have data for both training our model and validating its performance. After splitting, we proceed to train our random forest model on the training data. It learns from this data to make predictions. Once the model is trained, we use it to predict outcomes based on the test set. Now that we have predicted results, we can calculate the accuracy. The accuracy score gives us a clear indication of how well our model is performing, computed as the ratio of correctly predicted observations to the total number of observations. Finally, we print the accuracy, which helps assess the effectiveness of our feature engineering and model training efforts in this process. Now let's implement the following lines of code to calculate precision and recall for our machine learning model. First, we import the necessary functions, precision score and recall score, from the sklearn metrics module, which are essential for evaluating our model's performance in a binary classification context. Next, we compute precision using the precision score function, which takes in the true labels from the test dataset, ytest, and the predicted labels from our model, ypred. This metric will give us a clear insight into the proportion of positive predictions that were indeed correct. Following this, we calculate recall through the recall score function in a similar manner. Recall evaluates how many actual positive instances our model successfully identified. This metric is critical, especially in fields like healthcare, where failing to predict a positive case can have significant repercussions. Finally, we print out both precision and recall in a formatted string to ensure clarity in our results. This concise representation helps us gauge how well the model is performing not just in terms of accuracy, but also in capturing the positive class effectively. Next, we will write the following code to calculate the F1 score, which is essential in assessing the balance between precision and recall in our model's predictions. We begin by importing the F1 score function from the sklearn metrics module to facilitate our calculation. Now let's see how we can implement this. We will compute the F1 score using the true labels from our test dataset, ytest, and the predictions made by our model, ypred. This line of code essentially captures the performance of our classification model by considering both the false positives and false negatives, providing a single, comprehensive measure of accuracy. Finally, we will print the F1 score, formatted to 2 decimal places. This succinct output allows us to quickly evaluate how well our model balances precision and recall, especially important in cases where classes are imbalanced. The result will serve as an important metric in our evaluation toolkit, guiding us toward making more informed tuning decisions based on the model's performance. Now let's implement the necessary steps to visualize the ROC curve and compute the AUC ROC score. First, we begin by calculating the predicted probabilities for our test dataset using the predict-proba method of our trained model. We focus on the probabilities of the positive class, which will be essential for our ROC curve. Following this, we utilize the ROC curve function from the sklearn library to compute the false positive rate, FPR, and true positive rate, TPR, at various threshold settings. This function generates the data points needed to plot the ROC curve. Next, we calculate the AUC area under the curve using the awk method. The AUC score quantifies the overall performance of the model across all thresholds, providing a single scalar value. Once we have our FPR and TPR, we can plot the ROC curve using matplotlib, with the x-axis representing the false positive rate and the y-axis displaying the true positive rate. Additionally, we include a diagonal line representing a random classifier, enhancing the visualization's interpretability. Finally, we set labels and a title to the plot, allowing for a clear representation of our model's classification performance. Now let's implement the following code snippet to perform hyperparameter tuning using grid search for our random forest model. We begin by importing the grid search CV module from sklearn model selection, which allows us to systematically explore combinations of hyperparameters. Next, we define paramgrid, a dictionary that specifies the hyperparameters we want to tune. In this case, we are focusing on n-estimators, which determines the number of trees in the forest, and max depth, which limits how deep each tree can grow. Our grid includes a variety of values for both parameters, ensuring a comprehensive search for optimal model performance. We then create an instance of grid search CV, passing in our base model, the paramgrid, a scoring metric set to F1 to evaluate performance, and specifying CV equals 3 for threefold cross-validation. This setup allows grid search to test different combinations of the specified parameters while splitting the training data into 3 parts to ensure robustness. Finally, we fit the grid search object to our training data, xtrain and ytrain, which triggers the exhaustive search process. After the search completes, we print the best parameters found, helping us identify the optimal configuration for our model based on the F1 score. This approach can significantly enhance our model's predictive capability by ensuring it is finely tuned to the dataset. Now let's implement the following code to perform a randomized search for hyperparameter tuning using randomized search CV. First, we define a dictionary called paramdist, which contains the hyperparameters we want to optimize. In this case, we are focusing on the n estimators, which represents the number of trees in the random forest, and max depth, which indicates the maximum depth of each tree. These parameters will guide the search for optimal values that enhance model performance. Next, we initialize the randomized search CV object, where we specify the model to be evaluated, the hyperparameter distributions to sample from, the number of iterations to perform, n iter, the scoring metric F1 score in this scenario, and the number of cross-validation folds, CV. Once this setup is complete, we fit the model using our training data. Finally, we print out the best parameters derived from the randomized search. This output will reveal the optimal combination of hyperparameters, enabling us to refine our model's capabilities efficiently and effectively, showcasing the power of this tuning approach in a time-efficient manner. Now let's implement the following code to validate the performance of our best-tuned model using the test set. We begin by retrieving the best estimator from our grid search results, ensuring we are using the model that has been optimized through hyperparameter tuning. Next, we make predictions on the test dataset, which is crucial for assessing how well our model generalizes to unseen data. To quantify the model's performance, we calculate several evaluation metrics: accuracy, precision, recall, and F1 score. Accuracy gives us a broad indication of how many predictions were correct. Precision and recall provide a deeper insight, revealing how effectively our model identifies positive cases and how many actual positives were missed. Finally, we compute the F1 score, which balances precision and recall, particularly important when dealing with imbalanced datasets. We then print the results in a clear format, presenting each metric as a percentage or a decimal value. This final evaluation step is essential. It not only confirms the effectiveness of our tuning strategies, but also allows us to make informed decisions for future model enhancements. In conclusion, mastering model evaluation and tuning strategies is the key to unleashing the potential of your machine learning models. By understanding and employing evaluation metrics such as accuracy, precision, recall, and AUC-ROC, and by leveraging powerful tuning methods like grid search and randomized search, you set yourself up for success. With these tools in your machine learning toolkit, you're well equipped to build models that not only perform better, but also make reliable predictions that can transform insights into actions. Thanks for joining me in this journey through model evaluation and tuning. Keep experimenting, stay curious, and happy. Advanced applications of machine learning demonstrate its versatility across diverse fields. In this session, we will delve into the fascinating world of machine learning applications, showcasing how this powerful technology is reshaping industries from healthcare to finance, entertainment to manufacturing, and beyond. So far, we covered the importance of model evaluation and the techniques for model tuning to optimize hyperparameters. Now we will explore advanced applications of machine learning, uncovering real-world examples and illustrating how to implement some of these applications using Python and scikit-learn. Now let's implement a logistic regression model to predict the presence of diabetes using a healthcare dataset. We start by importing the necessary libraries, which include pandas for data manipulation and scikit-learn modules for model training and evaluation. Next, we load our hypothetical healthcare dataset containing health metrics for various patients. This dataset includes features such as age, BMI, and blood pressure, which are crucial for our model to assess diabetes risk. After defining our features X and the target variable Y, we split the dataset into training and testing sets. This allows the model to learn from one part of the data while the other part tests its performance. Moving forward, we instantiate the logistic regression model and fit it to our training data. Once trained, we make predictions on the testing set. To evaluate our model's performance, we employ a confusion matrix and a classification report, which provide insights into how accurately the model predicts diabetes presence. This analysis not only showcases the model's effectiveness, but also demonstrates the potential for machine learning to enhance patient care through better predictive capabilities. Now let's implement a decision tree classifier to detect fraudulent transactions based on a hypothetical dataset. We begin by loading the dataset containing transaction information, ensuring it includes essential features like transaction amount, location, and user ID, which are critical in identifying fraud patterns. Next, we separate our features and target variable, where our features comprise the transaction details, and the target variable indicates whether a transaction is fraudulent. To ensure our model generalizes well, we split the dataset into training and testing sets, reserving 20% for evaluation while using the remainder to train the model. Now let's create our decision tree model. We instantiate the decision tree classifier and fit it to our training data. This process allows the model to learn from the historical transaction patterns that may signal fraud. Once the model is trained, we will make predictions on the test set to evaluate its performance. We will utilize a confusion matrix and a classification report to assess the model's accuracy and effectiveness in detecting fraudulent transactions, providing insights into its performance metrics like precision, recall, and F1 score. Now let's see how we can implement a collaborative filtering recommendation system using the nearest neighbors algorithm. First, we start by loading a dataset that contains user ratings for various movies, which will serve as the foundation for our recommendations. To make this data easy to work with, we create a pivot table, arranging the data so that each row represents a user and each column represents a movie, with the corresponding ratings filled in. Missing ratings are replaced with zeros to indicate unrated movies. Next, we fit the nearest neighbors model to our pivot table using a cosine distance metric for similarity measurement. This model identifies users whose movie ratings are similar to the target user. Now, we can obtain movie recommendations for a specific user by defining their index in our dataset. The model will then find the nearest neighbors, or most similar users, based on the ratings they have given. Finally, we display the recommended movie IDs for the user based on the preferences shared by similar users, enhancing the experience by offering personalized viewing suggestions. This approach not only boosts user engagement, but also contributes to increased subscriptions on streaming platforms. Now let's see how we can implement a support vector machine (SVM) model for predictive maintenance using sensor data. First, we load our hypothetical dataset that contains sensor measurements for machinery, such as temperature, vibration, and pressure, which helps in assessing equipment health. We define our features with X maintenance, targeting the failure column as the variable to predict, denoted by Y maintenance. Next, we split this dataset into training and testing subsets, ensuring we use 80% of the data to train our model and reserve 20% for evaluation. This is crucial as it helps us assess the model's performance on unseen data. After the data preparation, we initialize an SVM model with a linear kernel, which is particularly effective for high-dimensional spaces, making it ideal for sensor data. We then fit the model to our training data, allowing it to learn the relationships between the features and the target variable. Finally, we use the trained model to make predictions on the test set. To evaluate its efficacy, we generate a confusion matrix and classification report, providing valuable insights into the model's predictive accuracy and performance metrics, which are vital for understanding how reliably it can anticipate equipment failures in real-world applications. Now let's implement a sentiment analysis model using the naive Bayes classifier, a powerful algorithm for text classification. First, we begin by loading a dataset containing customer reviews and their corresponding sentiment labels, where the reviews will serve as our features and the sentiments as our target variable. Next, we utilize the count vectorizer from scikit-learn, which is crucial for transforming our text data into a numerical format that machine learning algorithms can work with. This transformation follows the bag of words approach, allowing us to create a matrix representing the frequency count of words across the reviews. We then split the dataset into training and testing sets, ensuring the model is trained on one subset while being evaluated on another to assess its performance accurately. After initializing and training the multinomial NB model with our training data, we can make predictions on the test set, which will provide insights into its accuracy. Finally, we evaluate our model's performance using a confusion matrix and a classification report to understand how well our sentiment analysis is performing. This process underlines the importance of text classification in deriving meaningful insights from unstructured textual data. Now let's take a look at how we can implement a convolutional neural network, CNN, for image classification using TensorFlow and Keras. First, we import the necessary libraries, including TensorFlow and its layers and models modules, which are essential for building our CNN architecture. Next, we prepare our dataset by assuming we have a set of images ready for classification. This preprocessing step would typically involve loading and normalizing our image data. We then build the CNN model using a sequential approach. Our model begins with a convolutional layer that applies filters to the input images, allowing it to learn spatial hierarchies in the data. We follow this with a max pooling layer to reduce the dimensionality of the feature maps, which helps in minimizing computation and avoiding overfitting. We then add another convolutional layer, followed again by max pooling, to further extract essential features. The flattened output is then fed into a dense layer that learns the representations, and finally we add an output layer with a sigmoid activation function, suitable for binary classification tasks like differentiating between two categories, e.g., objects on the road. After defining the architecture, we compile the model with an atom optimizer and binary cross-entropy loss function, setting the stage for training. Finally, we fit the model on our image dataset, specifying the number of epochs and batch size to train the CNN on recognizing patterns in the images, thereby enhancing our autonomous vehicle navigation capabilities. As we venture further into the advanced applications of machine learning, it's clear that the future is bursting with potential. Whether it's enhancing healthcare, fortifying finance, enriching entertainment, optimizing manufacturing, comprehending language, or automating mobility, machine learning is at the forefront of innovation. In this session, we uncovered how machine learning transforms our world, illustrating the breadth and depth of its applications. We've seen practical examples using Python and scikit-learn to ground these concepts in reality. Grasping the power of machine learning opens up a realm of opportunities, inviting you to dive deeper and explore innovative solutions to real-world challenges. So, as you continue your journey into the captivating universe of machine learning, consider how you can apply these advanced techniques to your own projects and endeavors. The possibilities are endless. Happy coding and stay curious. Now let's dive into the realm of advanced data analysis techniques. While basic data analysis transforms raw data into a format suited for building models, advanced techniques unlock deeper insights and enable more complex and accurate predictions. Today, we will explore an array of advanced methods, focusing on their applications, how to implement them using Python and scikit-learn, as well as the insights they can provide. So far, we covered the diverse applications of machine learning, emphasizing its impact across healthcare, finance, entertainment, manufacturing, and natural language processing. We explored logistic regression, decision trees, and collaborative filtering techniques, among others. We have seen how machine learning transforms industries and enhances innovation. Now we will explore advanced data analysis techniques, highlighting their significance in refining model performance and accuracy. Next, we will implement the feature engineering process by working with a basic dataset that contains timestamp information. First, we import the necessary libraries, such as pandas for data manipulation and datatime for handling date and time objects. We create a simple data frame with a column called timestamp that holds string representations of date and time. Now, let's see how we can transform this raw timestamp data into a more manipulable format. We start by converting the timestamp column into pandas datatime objects, which allows us to access various attributes related to date and time. Once we have our timestamps in the correct format, we derive new features from the data. We extract the hour of the day and the day of the week from each timestamp, storing them in new columns, hour and day of week. Additionally, we create a binary variable called isWeekend to indicate if the date corresponds to a weekend based on the day of the week. This new variable can be quite valuable, as it helps the model capture temporal patterns that might influence predictions. Finally, we print the data frame to visualize the newly created features alongside the original data, enhancing our dataset for future analyses. Now let's see how we can implement a random forest model in Python using scikit-learn, which is particularly effective for classification tasks. We start by defining our feature set and target variable, where we extract the hour and isWeekend columns from our data frame to serve as predictors. The binary target variable y indicates the outcome we aim to predict. Next, we split the data into training and testing sets using a 66%-34% ratio, which enables us to train our model on one subset while validating its performance on another unseen subset. Once the data is split, we initialize the random forest model by specifying 100 trees, a good balance that often yields strong predictions without overfitting. We fit our model to the training data, allowing it to learn from the patterns present. After training, we generate predictions on our test set and evaluate the model's accuracy using the accuracy score metric. This score provides insight into how well our model performs by calculating the proportion of correct predictions. By employing random forests, we harness the power of ensemble learning, enabling our model to produce robust and reliable predictions. Next, we will explore how to optimize our random forest model through hyperparameter tuning using grid search. In our code, we first import the necessary grid search CV class from the SCIKIT model selection package. We then define a parameter grid that specifies the hyperparameters we wish to optimize, including n estimators, max depth, and min sample split. Each parameter is assigned a list of potential values to test during the tuning process. Next, we instantiate the grid search CV, passing our random forest classifier as the estimator and defining the parameter grid we just established. We also set the scoring metric to accuracy and specify a number of cross-validation folds, CV equals 3, to evaluate our model's performance robustly across different subsets of data. After setting up the grid search, we call the fit method with our training data, which initiates the hyperparameter tuning process. Once the grid search is completed, we can extract and display the best hyperparameters using grid search best params. This step is crucial as it allows us to fine-tune our model, enhancing its predictive power and ensuring better generalization to unseen data. Now let's implement the following code to demonstrate principal component analysis, PCA. We start by importing the PCA class from the SCIKIT decomposition module, which houses our dimensionality reduction technique. Next, we define an example dataset X comprising multiple two-dimensional data points. This dataset serves as our input for PCA, where we aim to reduce its dimensions while preserving variance. We then create an instance of the PCA class, specifying n components equals 1 to indicate that we want to reduce our dataset to one dimension. By focusing on a lower dimension, PCA helps capture the direction of maximum variance, which is crucial for simplifying our data without losing significant information. Afterward, we call the fitTransform method on our dataset X, which computes the principal components and transforms the dataset to the new reduced dimensions. The result, stored in XReduced, reflects our original data condensed into a single dimension, while retaining as much variance as possible. Finally, we print the reduced dimensions, allowing us to see how effective PCA has been in simplifying our data for analysis or visualization. Now let's implement the following code to evaluate the performance of our random forest classifier using key model evaluation metrics. First, we generate a confusion matrix, which provides a clear summary of the classification results by showing the counts of true positive, true negative, false positive, and false negative predictions. This matrix allows us to quickly assess how many instances were correctly or incorrectly classified, offering insights into the areas where our model may be underperforming. Next, we produce a classification report that includes important metrics such as precision, recall, and the F1 score. Precision indicates the accuracy of the positive predictions, while recall measures the model's ability to identify all relevant instances. The F1 score, the harmonic mean of precision and recall, provides a balanced measure when dealing with uneven class distributions. Displaying this information helps us understand not only how well the model performs in general, but also how it behaves with respect to the classes involved, giving us a comprehensive view of its performance and areas for improvement. Together, these metrics are crucial for refining our models and ensuring they meet the desired effectiveness in crucial applications. In conclusion, advanced data analysis techniques are essential for extracting richer insights from data. Feature engineering sets the stage for better model performance, while ensemble methods like random forests elevate predictive accuracy. Hyperparameter tuning ensures that our models operate at peak performance, and dimensionality reduction techniques like PCA simplify complex datasets. Finally, robust model evaluation metrics guide us in interpreting our model's effectiveness. As we pave the way for further exploration in the world of machine learning, remember, data is our canvas, and advanced techniques are the brushes that delineate patterns, shape insights, and empower decisions. With the skills acquired in this lesson, you now hold the keys to unlock the potential within your data, revealing stories and insights waiting to be discovered. In today's lesson, we'll delve into the fascinating applications of machine learning across various industries. Machine learning is not just a trendy buzzword, it's a cornerstone of innovation and efficiency, enabling businesses to harness data in powerful ways. So far, we learned about advanced data analysis techniques that enhance model performance and predictive accuracy. We covered feature engineering, transforming raw data into meaningful features, and explored ensemble methods like random forests for robust predictions. Additionally, we discussed hyperparameter tuning using grid search for optimal model performance, the importance of PCA for dimensionality reduction, and various evaluation metrics to assess model effectiveness. These concepts empower us to extract deeper insights from data and improve decision-making in machine learning applications. Now, we will cover the specific ways machine learning is changing industries like healthcare, finance, entertainment, and manufacturing. Now let's see how we can implement a convolutional neural network, CNN, to classify chest X-ray images. First, we import the necessary libraries from TensorFlow and Keras, which provide pre-built layers for constructing our model. We then initialize a sequential model, which allows us to stack layers linearly. Next, we add several convolutional layers, which are crucial for feature extraction from images. Each convolutional layer applies filters to the input image, detecting patterns such as edges or textures, and using the ReLU activation function to introduce nonlinearity. After each convolutional layer, we employ max pooling layers to downsample the feature maps, reducing dimensionality while retaining important information. Once we have extracted the features, we flatten the output from the last pooling layer into a single vector to feed into the dense layers. The first dense layer further processes the extracted features with another ReLU activation, and the final dense layer uses a sigmoid activation function to output a probability for binary classification, determining whether an X-ray shows signs of pneumonia or not. Lastly, we compile the model with the Atom optimizer and specify the binary cross-entropy loss, suitable for our binary classification task, along with accuracy as the evaluation metric. Now let's see how we can implement a logistic regression model to predict whether patients will be readmitted based on specific features from a dataset. First, we import the necessary libraries for data manipulation, model training, and evaluating accuracy. We create a small dataset that includes patient age, previous health conditions, and whether they were readmitted, which will serve as our input features and target variable. Next, we convert this dictionary into a pandas data frame for easier data handling and analysis. The features are stored in a variable x, which consists of age and previous conditions, while y holds the target variable readmitted. We split this dataset into training and testing sets, allocating 20% of the data for testing to assess the model's performance later on. Now we instantiate the logistic regression model and fit it using the training data, allowing it to learn the relationship between the features and the likelihood of readmission. Finally, we use the model to make predictions on the test set and calculate the accuracy of these predictions, thus providing insight into the model's effectiveness in forecasting patient outcomes. This approach demonstrates how predictive modeling can enhance patient care by enabling timely interventions. Now let's see how we can apply the isolation forest algorithm to identify potentially fraudulent transactions within our dataset. First, we import the necessary isolation forest class from the SCIKIT ensemble module, which is specifically designed for detecting anomalies. We create a sample dataset representing transaction amounts, where most transactions fall within a normal range, except for a few outliers, such as a significantly larger transaction of 2,000. Next, we initialize the isolation forest model, specifying a contamination parameter to indicate the expected proportion of outliers in the dataset. In this case, we set it to 0.1, meaning we anticipate around 10% of the transactions to be anomalous. After fitting the model to our transaction data, we proceed to predict which transactions are likely to be anomalous. The predict method assigns a value of -1 to transactions identified as outliers and 1 to those deemed normal, allowing us to easily flag potentially fraudulent activities. Finally, we print the predictions to examine which transactions are flagged for further investigation. Implementing this anomaly detection technique enables banks to proactively address fraud, significantly reducing financial risks associated with fraudulent transactions. Now let's see how we can implement a linear regression model to predict stock prices based on historical data. First, we import necessary libraries such as NumPy and Pandas for data manipulation, and the train test split and linear regression classes from scikit-learn for our model. We start by creating a sample dataset, where day corresponds to the trading days and price indicates the stock prices. This data is then transformed into a data frame for easier handling. We split our data into features x and the target variable y, enabling us to train our model. The train test split function helps us to segment the dataset into training and testing subsets, ensuring that our model can be evaluated effectively after training. Next, we initialize our linear regression model and fit it to the training data, allowing the model to learn the relationship between the features and stock prices. Finally, we use the trained model to make predictions on the test set and print out the predicted stock prices. This process exemplifies how traders can leverage machine learning to make informed, data-driven decisions in real time based on historical trends. Now let's see how we can implement user-based collaborative filtering in our recommendation system. We begin by importing the necessary libraries, specifically pandas for data manipulation and Sklern's cosine similarity function to measure the similarity between users based on their ratings. Next, we create a sample dataset that represents user ratings for various items. Each user has rated items on a scale, with a 0 indicating that the item hasn't been rated. We store this data in a pandas data frame, which allows us to manipulate and analyze the data efficiently. Once our dataset is ready, we proceed to calculate the cosine similarity between users, filling in any missing ratings with zeros to ensure accurate comparisons. The cosine similarity metric helps us understand how similar users are based on their rating patterns. This matrix of similarities acts as the backbone of our recommendation engine. Finally, we print the computed similarity matrix, which will show how closely related the users are to one another. This information is essential for suggesting items to users based on the preferences displayed by others with similar tastes, ultimately enhancing user engagement with the platform. Now let's see how we can implement a machine learning model to predict equipment failure in manufacturing settings. We start by importing the necessary library, Decision Tree Classifier, from the scikit-learn library, which will allow us to build our decision tree model. Next, we create a dataset containing operational data, which includes features such as temperature, vibration, and operating hours, as well as a target variable indicating whether a failure occurred. After organizing our data into a pandas data frame, we separate the features and target variable into distinct sets, with X containing the feature columns and Y representing the failure outcomes. Now we proceed to initialize the decision tree classifier and fit it to our operational data using the fit method, enabling the model to learn and understand the relationships between the features and the likelihood of failure. Finally, we demonstrate how to make predictions by feeding new operational data points into the model. The predicted output will help manufacturers identify whether equipment is likely to fail, thus allowing them to schedule maintenance proactively and avoid unexpected breakdowns. This implementation is a crucial step in enhancing operational efficiency and reducing costs in the manufacturing industry. As we wrap up our journey through the applications of machine learning across various industries, it's clear that the impact of this technology is profound. From enhancing medical diagnostics to predicting stock prices, from personalizing user experiences to optimizing manufacturing processes, machine learning is reshaping how we approach data-driven decision-making. The versatility of machine learning applications allows companies to leverage data effectively, yielding insights and fostering innovation that drive success. As we move forward, developing an understanding of the specific methodologies and technologies available will empower you to harness the potential of machine learning in your own career or projects. So the next time you're enjoying a movie recommended by your streaming service, or your bank alerts you of potentially fraudulent transactions, remember that behind the scenes, machine learning algorithms are silently at work, making our lives easier and more efficient. Embrace this powerful technology as it continues to grow and unleash its potential in your own Now let's implement a simple text generation model using the Transformers library in Python, which demonstrates the power of natural language processing. First, we start by importing the necessary classes, GPT-LM head model and GPT tokenizer, from the Transformers library. These will allow us to leverage the pre-trained GPT-2 model for generating human-like text. Next, we load the pre-trained model and tokenizer, which have been trained on a vast corpus of text to understand context and generate coherent language. After that, we define our input text, which serves as a prompt for the model. We encode this prompt into input IDs using the tokenizer, preparing it for the model. Now let's see how we can generate an output sequence using the model. By calling the generate method with specified parameters such as max length, we can control the length of the generated text. Finally, we decode the output back into a human-readable format and print it. The generated text exemplifies how far AI has come in generating meaningful language, paving the way for more sophisticated applications in chatbots and virtual assistants. Now let's dive into an example that employs a decision tree classifier to predict a user's favorite recipe based on the ingredients they have available. First, we set up our data, representing various ingredients along with the corresponding favorite recipes. This dataset is encapsulated in a pandas data frame, allowing us to easily manipulate and analyze the information. Next, we specify the features, the ingredients, and the target variable, the favorite recipe, from our data frame. Since decision tree classifiers require numerical input, we need to encode these categorical features using one-hot encoding via the getDummies function. This transforms our ingredients into a format the model can understand. Following this, we split our dataset into training and testing sets, ensuring our model can learn from the training data while maintaining the integrity of the test set for evaluation. With the data prepared, we proceed to create and train our decision tree classifier model, allowing it to learn the relationships between ingredient combinations and their corresponding recipes. Finally, we predict a favorite recipe based on a sample input of ingredients. The model returns the predicted recipe, showcasing how AI can simplify cooking decisions in an increasingly smart and integrated kitchen environment. Now let's see how we can implement a basic logistic regression model to predict loan approval based on the applicant's age and income. We start by importing necessary libraries, including pandas for data manipulation and sklearn for machine learning functionalities. Next, we simulate a dataset comprising sensitive attributes such as age, income, gender, and loan approval status. We create a pandas data frame from this data, which we will use to separate our features, age and income, from the target variable, loan approval. To prepare our data for model training, we split the dataset into training and testing sets using the trainTestSplit function, ensuring a random state for reproducibility. Following the data preparation, we instantiate a logistic regression model and fit it using our training data. This process involves the model learning patterns in the data to make predictions. Once the model is trained, we use it to predict loan approvals on our test set. Finally, we calculate and print the accuracy score, providing insight into how well our model performs on unseen data. This emphasizes the importance of evaluating model fairness alongside accuracy to ensure equitable treatment across demographic groups. Let's implement a simple simulation of a robotic arms functionality using Python. In this code, we create a robotic arm class that encapsulates the behaviors and states of the arm. The init method initializes the arm's position to ready and sets a flag, object present, to track whether an object is detected. Next, we define the pickup method, which checks if an object is present before changing the arm's position to holding object. If no object is detected, it provides feedback indicating that there's nothing to pick up. Similarly, the placedown method assesses if the arm is currently holding an object. If so, it returns the arm to the ready position. If not, it informs the user that there isn't an object to place down. Lastly, we include a detectObject method that updates the object present flag to true, simulating the detection of an object. After creating an instance of the robotic arm and calling these methods, we can observe the arm's interactions through the console. This paradigm lays the groundwork for understanding more complex robotic systems and their automation capabilities. Now let's implement a basic anomaly detection model using the DBSCAN algorithm, which is particularly effective for identifying clusters and outliers in data. We begin by importing the necessary libraries, DBSCAN from sklearn, cluster, for our clustering algorithm, and NumPy for numerical operations. Next, we simulate user behavior data, specifically user login times, by creating a NumPy array with various timestamps. The DBSCAN algorithm requires us to specify its parameters, EPS, which defines the maximum distance between two samples to be considered in the same neighborhood, and min samples, indicating the number of points required to form a dense region. In this example, we set EPS to 1.5 and min samples to 2, fine-tuning it to identify anomalies effectively. After configuring our model, we apply the fitPredict method to our simulated data, which classifies each data point as part of a cluster or as an anomaly, returning an array of labels. Finally, we print the results, revealing insights into the detected anomalies, which may indicate unusual login behavior that could signify potential security threats. This approach demonstrates how AI can proactively safeguard against cybersecurity challenges. Now let's implement a simple recommendation system that personalizes education by analyzing user cost ratings. First, we begin by importing the pandas library, which will help us manage our data efficiently. We then create a sample dataset represented by a dictionary, where each user's ratings for different courses are stored. The ratings range from 0 to 5, where 0 signifies no rating. Next, we convert this dictionary into a pandas data frame, with course names as the index, allowing us to easily manipulate and analyze the data. To assess the similarities between courses based on user ratings, we utilize the cosine similarity metric. This method helps us understand which courses tend to be liked together by comparing the angle between the vectors of their ratings. We fill any missing ratings with zeros using the Filner method, ensuring that all data points are considered in our analysis. Finally, we calculate the cosine similarity and store it in a variable, which we then print. This output serves as the foundation for a recommendation engine, enabling the learning platform to suggest study materials tailored to each student's preferences. As we've discussed, the potential future developments in artificial intelligence are both thrilling and transformative. From advanced natural language processing and the integration with IoT to ethical considerations, robotics, cybersecurity, and personalized education, the opportunities abound. The fusion of AI into various sectors will reshape how we live, work, and learn. Collectively, these advancements will not only enhance efficiency and decision-making, but also present new challenges and responsibilities. As we venture into this exciting future, it is crucial for us, developers, researchers, and users, to approach AI with an awareness of its implications. By embracing ethical practices, prioritizing transparency, and ensuring fairness, we can harness the power of AI for good. So as we stand on the cusp of this remarkable era in technology, let us remain inquisitive and committed to making AI innovations a force for positive change. The future of artificial intelligence is not just about smarter machines, it's about forging a smarter society. Embrace this journey, be part of the conversation, and actively contribute to shaping the future of AI. From the perspective of real-world machine learning, there are several challenges that practitioners must navigate. Understanding these challenges is essential for anyone looking to delve into the complexities of machine learning. In this video, we'll explore the significant hurdles faced in the implementation and application of machine learning models, ranging from data-related issues to algorithmic complexities. So far, we covered the promising future of artificial intelligence, explored key areas such as natural language processing, AI integration with IoT, and the critical importance of ethics in AI development. We discussed the various applications of machine learning in sectors like healthcare, finance, and education, while highlighting the necessity of mitigating bias in AI systems. Moving forward, we will talk about the challenges encountered in machine learning and how these challenges can be addressed effectively. Now let's implement the following code to merge multiple datasets using the Pandas library, which is vital for ensuring that we have a unified view of our data prior to further analysis. We start by importing the Pandas library, which provides powerful tools for data manipulation. The next step involves loading our datasets, activity logs, CSV, and support logs, CSV. This is done using the PD read CSV function, allowing us to read in our data files into data frames. After loading the datasets, we need to merge them based on a common identifier, which in this case is customer. Merging is crucial when dealing with customer data from different sources. It allows us to combine relevant information into a single data frame. We accomplish this using the PD merge function, specifying the customer as the key. The how equals inner parameter ensures that only matching records from both datasets are included in the merged dataset. Finally, we display the first few rows of the merged dataset with the print function, providing a quick view of how our data looks after combining the two sources. This preparation is essential to enable our machine learning model to analyze the information effectively and draw meaningful insights. Next, we will implement a method for checking and handling missing values in our merged dataset. First, we use the isNull function followed by sum to identify and summarize the number of missing entries in each column of the data frame. This step is crucial because it provides insight into data quality, which directly impacts model training. Understanding where the gaps are enables us to make informed decisions about how to address them. Once we have the summary of missing values, we proceed to clean our data by removing entries where the target variable, customer churn, is missing. Since these specific entries do not provide useful information for training our model, we apply the dropner function with the subset parameter targeting the target column. This ensures we retain only the rows that have complete information for our prediction task, thereby enhancing the dataset's overall integrity. Clean data is foundational in building reliable machine learning models, and this code snippet effectively addresses one of the critical aspects of data cleaning. Now let's implement the following code to build our classification model using scikit-learn. We start by preparing our features and labels, where the features are the selected columns from our clean dataset, and the target variable is what we want to predict. Next, we split the dataset into training and testing sets using the train-test-split function, which ensures that 20% of the data will be reserved for testing. This random split helps assess the model's performance on unseen data, allowing us to determine how well it generalizes. Following this, we create an instance of the support vector classifier, a popular model for classification tasks due to its high performance in dealing with complex datasets. We then fit this model to our training data, enabling it to learn the patterns associated with our features and target labels. Finally, we use the trained model to make predictions on the testing set. The predictions generated will be compared against the actual labels to evaluate the model's accuracy. This process illustrates the foundational steps of training a machine learning classifier and sets the stage for further evaluation and optimization of the model's performance. Now let's implement recursive feature elimination with cross-validation using scikit-learn to identify the most impactful features for our model. We begin by importing RFECV from the SCIKIT feature selection module, which facilitates the recursive elimination of features by using cross-validation to determine which combination yields the best model performance. First, we initialize a logistic regression model, which will serve as our estimator in the feature selection process. Following this, we create an instance of RFECV, specifying our model, a step value of 1 to remove one feature at a time, and a cross-validation parameter set to 5. This means we will evaluate our feature set over 5 distinct training and validation splits of the data. Next, we fit the selector using our training data. This step automatically selects and ranks the features based on their contribution to the model's accuracy. After fitting, we can extract the selected features through the support attribute, which provides a Boolean mask indicating the chosen features. Finally, we print the names of the selected features, offering insights into which variables have the most influence on our model's predictions. This technique not only streamlines the feature selection process, but also enhances model interpretability and performance. Now let's see how we can evaluate different classifiers for our customer churn prediction task. We start by importing the accuracy score function from the SCIKIT metrics module, which will help us measure the performance of our classifiers. Next, we create a dictionary named classifiers that holds 2 machine learning algorithms, logistic regression and support vector classifier. This structure allows us to easily iterate through our chosen models. As we move forward, we will implement a loop that processes each classifier in our dictionary. For every classifier, we fit the model to our training data using fit, after which we make predictions on the test data with the predict method. To evaluate how well each classifier performs, we calculate the accuracy by comparing the predicted results against the actual outcomes in the test set via accuracy score. Finally, we print the accuracy of each model in a formatted output, providing a clear comparison of their effectiveness in predicting customer churn. This step is crucial in identifying the algorithm that best suits our specific problem and data characteristics. Now let's see how we can implement ridge regression to combat overfitting in our model. We start by importing the ridge class from the SCIKIT linear model module, which allows us to create a ridge regression model that incorporates L2 regularization. This regularization technique adds a penalty equivalent to the square of the magnitude of coefficients, preventing them from becoming too large and thus helping reduce overfitting. Next, we initialize our ridge regression model with an alpha parameter set to 1. This hyperparameter controls the amount of regularization applied. Higher values increase the penalty on coefficients. Following this, we fit our ridge model using the training data, which enables it to learn the underlying patterns associated with our features and target variable. Once the model is trained, we generate predictions on the test dataset, which consists of unseen data. Finally, we calculate the accuracy by comparing the predicted values against the actual targets in the test set. Printing the accuracy gives us insights into the model's performance, allowing us to evaluate its effectiveness relative to previous classifiers we've explored. Next, we will implement SHAP to enhance the interpretability of our machine learning model. To begin, we import the SHAP library, which is designed to explain the output of machine learning models by assigning each feature an importance value. We then create an explainer object by passing in our trained model and the training dataset. This explainer will help us understand the model's predictions by calculating SHAP values for the test dataset, which represent the contribution of each feature to the predictions. Now let's visualize the explanation for the first prediction in our test set. By initializing the JavaScript visualization with SHAP init, we set up an interactive display to help us interpret the results effectively. The SHAP forceplot function takes the expected value of the model's output, the SHAP values for the first instance, and the features of that instance to generate a force plot. This plot beautifully demonstrates how each feature positively or negatively influences the predicted outcome, allowing stakeholders to grasp the decisions made by the machine learning system clearly. This transparency is vital, especially in domains where understanding the rationale behind predictions can significantly impact trust and decision-making processes. Now let's implement a simple Flask application to expose a prediction endpoint for our machine learning model. We begin by importing the necessary libraries: Flask for creating the web application, Request for handling incoming requests, and JSONify to convert responses into JSON format. Next, we instantiate a Flask app by creating an object of the Flask class. To make our model accessible, we load it from a file named model, pkl, using the joblib library, which is excellent for serializing Python objects, particularly large NumPy arrays, such as those found in machine learning models. Now let's create a route for our prediction endpoint. We define a function called predict that responds to post requests. Within this function, we extract the incoming JSON data and specifically grab the features necessary for making a prediction. The model then processes this data, and we return the prediction as part of a JSON response, where the predicted value is easily accessible for other applications. Finally, we enable the app to run in debug mode, which is useful for development, as it provides detailed error messages to help troubleshoot any issues. This basic Flask application sets the foundation for integrating our machine learning model into real-world applications. In summary, we have explored several major challenges in machine learning, including date-related issues, model selection, overfitting, interpretability, and deployment. Understanding these hurdles is crucial for practitioners looking to succeed in the field. As we continue our journey in machine learning, remember, every challenge presents an opportunity to refine, innovate, and enhance our approaches. In the next lesson, we will discuss advanced techniques to handle some of these hurdles effectively and delve into optimizing machine learning models. Thank you for joining me today, and I look forward to seeing you in the next. Now let's see how we can implement hyperparameter tuning using grid search with a random forest model. First, we begin by importing the necessary classes from SCIKIT Learn, random forest classifier for the model and grid search CV for hyperparameter tuning. After initializing the random forest classifier model, we need to define a parameter grid that specifies the hyperparameters we want to optimize. In this case, we include n estimators, which determines the number of trees in the forest, max depth, which limits how deep each tree can grow, and min sample split, which dictates the minimum number of samples required to split an internal node. Next, we set up the grid search CV, providing it with our model and the defined parameter grid. We also specify that the model should be evaluated using threefold cross-validation and allow the process to utilize all CPU cores for efficiency. Upon fitting the grid search to our training data, it will iterate through all combinations of the specified hyperparameters to identify the set that yields the best performance. Finally, we can easily extract and print the best parameters found, which will be crucial as these parameters can significantly enhance how well our model performs on unseen data. Now let's see how we can implement feature engineering to enhance our dataset. First, we import the pandas library, which is essential for data manipulation and analysis. We then create a sample data frame containing customer information, including a unique customer ID, their join date, and the total amount they have spent. Next, we derive a new feature called membership duration, which calculates the number of days each customer has been a member by subtracting the join date from today's date. This metric can be a strong indicator of customer loyalty, providing insights into how long customers have been associated with the business. Additionally, we categorize customers into spending categories using the spending category feature. Here, we utilize the pd_cut function to segment the total spent values into 3 bins: low, medium, and high. This categorization helps us to better understand customer segments based on their spending behavior. Finally, we print the data frame, which now includes these valuable new features, demonstrating how effective feature engineering can improve the model's performance by incorporating more meaningful attributes. Now let's see how we can implement an ensemble method using random forest, a powerful technique for classification tasks. We begin by importing the necessary classes from SCIKIT Learn, specifically the random forest classifier, for our model and accuracy score to evaluate its performance. Next, we instantiate the random forest model with the n estimate as parameter set to 100, meaning the model will use 100 decision trees to make predictions. This multitude of trees enhances the model's ability to generalize to new data by averaging the predictions, thus reducing the risk of overfitting. After creating the model, we fit it to our training data using the fit method, which allows the model to learn from the input features and the corresponding target labels. Once trained, we use the predict method to make predictions on the test set, generating an array of predicted labels. Finally, we assess the model's accuracy by comparing the predicted labels with the actual labels from the test set using the accuracy score function. Printing the accuracy provides insight into how well our random forest model performed, showcasing the efficacy of ensemble methods in improving prediction accuracy. Now let's see how we can implement lasso regression to enhance our model's performance through regularization. We begin by importing the necessary libraries, specifically lasso from the SCLearn linear model module for creating our regression model, and mean squared error from SCLearn metrics to evaluate its performance. Next, we create an instance of the lasso regression model, specifying the alpha parameter at 0.1. This parameter controls the strength of the regularization. Higher values apply more penalty on the coefficients, effectively discouraging complex models that may overfit on the training data. After instantiation, we fit the model to our training data, allowing it to learn the underlying patterns. Once fitted, we use the model to make predictions on the test set. The predictions are then evaluated using the mean squared error metric, which quantifies the difference between the actual and predicted values. Finally, we print out the mean squared error, giving us insight into how well our lasso regression model performed. This step not only helps in assessing model accuracy, but also illustrates the impact of regularization techniques in managing complexity and improving interpretability. Now let's see how we can evaluate our model using important classification metrics. First, we will utilize the classification report function from scikit-learn, which summarizes key classification metrics including precision, recall, and F1 score. This report provides a detailed breakdown of our model's performance across different classes, helping us identify strengths and weaknesses in our predictions. Next, if our random forest model outputs probability predictions, we can assess its efficacy with the ROC-UC score. To implement this, we need to obtain the predicted probabilities of the positive class using the predict-proba method. This gives us a continuous score indicating the likelihood of each instance belonging to the positive class. By passing these probabilities to the ROC-OC score function along with the true labels, we can compute the area under the ROC curve, a vital metric for understanding how well our model separates classes. Evaluating model performance through these metrics enables us to make informed decisions on improvements and adjustments, ensuring our model meets the desired performance standards. Next, we will implement k-fold cross-validation to evaluate our random forest model's performance. First, we import the cross-val score function from scikit-learn, which facilitates the cross-validation process effortlessly. This function will help us assess the model's stability and generalizability by dividing the training data into 5 subsets or folds. The model trains on 4 of these subsets while testing on the remaining one. We assign the results from cross-val score to the variable scores, where each score corresponds to the model's performance on the held-out fold. Finally, we print the individual cross-validation scores, allowing us to see how the model performs across different partitions of the data. To provide an overall assessment of our model's capabilities, we compute and print the average of the cross-validation scores. This average score serves as a reliable indicator of the model's expected performance on unseen data, ensuring we are prepared for real-world applications. By consistently applying cross-validation, we can make informed decisions about further optimizations needed for the model. Now let's implement a pipeline in scikit-learn that integrates data scaling and model training into a single, efficient workflow. We start by importing the necessary classes, pipeline from the SCLearn, pipeline module and standard scaler from SCLearn preprocessing. Next, we create a pipeline object that consists of 2 steps. The first step is to apply the standard scaler, which standardizes the features by removing the mean and scaling to unit variance. This preprocessing step is crucial as it ensures that the input features have a consistent scale, which can enhance the performance of many machine learning algorithms, including our classification model. Following the scaling step, we add a classification step using the random forest classifier with 100 trees. This classifier will leverage the scaled data to make predictions. After defining the pipeline, we fit it on the training data using the fit method. This action triggers the entire pipeline. The data is scaled, and the model is trained in one seamless process. Finally, we use the pipeline to make predictions on the test data, followed by evaluating the accuracy of the model. This pipeline approach not only simplifies the code, but also minimizes the risk of data leakage, ensuring a clean and efficient evaluation of your model. In conclusion, advanced techniques such as hyperparameter tuning, feature engineering, ensemble methods, regularization, evaluation metrics, cross-validation, and pipelines are crucial for enhancing model performance. Each of these techniques addresses various aspects of model training and evaluation, helping to optimize our machine learning workflows. As you continue your journey in machine learning, remember that a thorough understanding and application of these advanced techniques can make a significant difference in achieving high-performing models. Stay curious, keep experimenting, and I look forward to our next adventure in machine learning. Machine learning has transformed industries by providing data-driven insights and automation capabilities. Today, we will explore a collection of successful implementations of machine learning across various sectors. In our previous sessions, we learned about improving model performance through advanced techniques such as hyperparameter tuning, feature engineering, and ensemble methods. We explored the importance of high-quality data, model selection, and evaluation metrics in enhancing machine learning workflows. Additionally, we discussed regularization techniques and the benefits of cross-validation for assessing model performance. Finally, we emphasized the role of pipelines in streamlining the modeling process and preventing data leakage. Now, let's delve into real-world case studies where machine learning solutions have brought about significant success. Next, we will write the following code to prepare our dataset for the random forest model, which helps predict flu outbreaks based on environmental factors. We start by importing the necessary libraries, including pandas for data manipulation and random forest classifier from scikit-learn for building our predictive model. Now let's see how we can prepare our sample dataset, which includes features such as temperature and humidity, along with historical flu cases. We create a data frame from a dictionary that contains this data. Once the data frame is set up, we need to split it into features and labels. The features are represented by the temperature and humidity columns, while the target variable is the flu cases column. To ensure our model can generalize well, we will divide our dataset into training and testing sets using the train-test-split function. This function randomly splits the data while maintaining a specified test size, enabling us to evaluate the model's performance later. Next, we will build and train the random forest classifier. By setting n estimators to 100, we instruct the model to utilize 100 decision trees for making predictions. Finally, we make predictions on our test set and print the results, allowing us to assess the model's effectiveness in predicting potential flu outbreaks based on environmental conditions. Now let's see how we can implement a simplified version of collaborative filtering using Python. We begin by importing the necessary libraries, specifically NumPy for numerical operations and cosine similarity from scikit-learn to compute user similarity scores. Next, we define a sample user-item interaction matrix, where each row represents a user and each column represents an item. The values indicate interactions, such as purchases or views, with 1 representing an interaction and 0 indicating none. This matrix lays the foundation for understanding user preferences based on their behaviors. Now, we calculate the similarity scores among users using the cosine similarity function. This function compares the user's interaction patterns and produces a similarity matrix, revealing how closely users resemble one another. Finally, we proceed to predict user 1's preferences by taking the dot product of user 1's similarity scores with the user item matrix. This step generates predicted preferences for various items that user 1 might enjoy, ultimately enabling personalized recommendations. By employing this collaborative filtering approach, we can enhance user experience through tailored suggestions based on similarities with other users. Next, we will implement a simple logistic regression model to identify fraudulent transactions based on transaction amount. First, we begin by importing necessary libraries, specifically pandas for data manipulation and scikit-learn for machine learning functionalities. Now let's set up an example transaction dataset represented as a dictionary containing transaction amounts and their corresponding labels indicating whether they are fraudulent or legitimate. We convert this dictionary into a pandas data frame for easier data handling. After structuring the data, we separate the dataset into features, the transaction amount, and the target variable indicating fraud. Next, we split our data frame into training and testing sets, using a stratified approach to ensure that both sets maintain the same proportion of classes, which is crucial for the model's performance. Once our data is prepared, we instantiate a logistic regression model and fit it with our training data. This step involves learning the relationship between the transaction amount and the probability of it being fraudulent. Finally, we make predictions on the test set and evaluate the model's accuracy, which gives us insights into the model's effectiveness in classifying transactions correctly. With this setup, we now have a basic fraud detection model to build upon. Now let's see how we can implement a simple neural network model to classify images of road signs using TensorFlow and Keras. We start by importing the necessary libraries, including TensorFlow and its Keras API for building neural networks. Next, we define our model architecture using the sequential API, which allows us to stack layers easily. The first layer is a flattened layer that transforms the input images, which are 28x28 pixels, into a one-dimensional array, making it suitable for processing by the subsequent dense layers. After that, we add a dense layer with 128 neurons and a RayLU activation function, which introduces nonlinearity and helps the model learn complex patterns. Finally, we include an output layer with 10 neurons and a softmax activation function, enabling the network to classify the input into one of 10 possible categories, corresponding to different road sign types. Following the model definition, we compile it using the Atom optimizer, which is effective for many problems, and specify the loss function as sparse categorical cross-entropy, suited for multi-class classification tasks. At this point, the model is ready to be trained on our dataset, which would involve calling the fit method with the training data. This foundational setup paves the way for our neural network to learn and accurately classify road signs. Now let's implement a simple linear regression model to forecast future sales based on historical data. First, we define our sample dataset, where we have sales data tracked over 5 weeks. The weeks array represents the time series aspect, while the sales array contains the corresponding sales figures for those weeks. Next, we create and train our linear regression model using the linear regression class from the scikit-learn library. The model learns the relationship between the weeks and sales, allowing it to identify trends and make predictions. After fitting the model with the provided data, we can predict sales for the next week by passing the new input value, representing week 6. Finally, we output the predicted sales value for week 6. This simple yet powerful approach aids retailers in anticipating demand, ensuring optimal inventory levels while enhancing customer satisfaction. By employing this model, businesses gain actionable insights, enabling them to respond quickly to market trends and improve operational efficiency. Now let's see how we can implement a linear regression model to predict crop yields based on environmental factors. We begin by importing the necessary libraries, specifically linear regression from SCIKIT linear model, which provides us with the tools for creating and training our regression model. Next, we construct a sample dataset representing various features that affect crop yields, including temperature, rainfall, and fertilizer use, along with the actual yield data. Using pandas, we create a data frame from this data, making it easier to manipulate and analyze. After preparing our dataset, we separate the features from the target variable. The features, temperature, rainfall, and fertilizer, are stored in variable X, while the yield data is stored in variable Y. This separation allows the model to learn from the effects of these features on yields. We then instantiate our linear regression model and fit it to our data, enabling it to learn the relationships between the features and the target. Finally, to predict future crop yields, we input new data representing weather conditions and fertilizer application. This predictive capability empowers farmers to make data-driven decisions, effectively improving their crop management and resource utilization. As we have explored various case studies across multiple industries, it is evident that machine learning is revolutionizing the way we operate in healthcare, e-commerce, finance, automotive, retail, and agriculture. These real-world applications showcase the transformative nature of machine learning, leading to enhanced decision-making and operational efficiencies. By harnessing the power of these technologies, industries are not only improving their processes but are also delivering remarkable value to their customers. As we conclude our discussion today, remember that the potential for machine learning is vast, and as technology evolves, so too will the capabilities and impact of these innovative systems. so stay curious and keep exploring the possibilities within the realm of machine. Implementing machine learning effectively requires adherence to best practices that ensure successful outcomes. In this lesson, we'll dive deep into these practices, enabling you to build robust and scalable machine learning models. So far, we learned that machine learning is revolutionizing various industries such as healthcare, e-commerce, finance, automotive, retail, and agriculture through data-driven insights and automation. We reviewed key techniques like hyperparameter tuning, feature engineering, and regularization, emphasizing their importance in model performance and evaluation. Additionally, we explored real-world applications, such as predictive analytics in healthcare and personalized recommendations in e-commerce, showcasing how these innovations enhance decision-making and operational efficiencies. Overall, machine learning is proving to be a transformative force across diverse sectors, providing significant value and insights. Now, we will cover best practices for implementing machine learning effectively. Now let's see how we can conduct exploratory data analysis, EDA, using Python's pandas and visualization libraries. First, we begin by importing the necessary libraries, pandas for data manipulation, and matplotlib and seaborn for data visualization. Next, we load our dataset from a CSV file into a pandas data frame, which allows us to easily manipulate and analyze the data. To understand the basic characteristics of our dataset, we print out descriptive statistics using the describe method. This step gives us insights into key metrics such as the mean, standard deviation, and quartiles of each feature, helping us identify any potential data issues at a glance. Following this, we create a correlation matrix that quantifies the relationships between different features in the dataset, which is crucial for feature selection later on. We then visualize this correlation matrix using Seaborn's heatmap function, which provides an intuitive graphical representation of how different features correlate with one another. The annotations on the heat map further enhance our understanding by revealing the strength and direction of these correlations. By following these steps, we are setting a solid foundation for the subsequent phases of model training and feature selection. Now let's implement a method to handle missing values and scale our features effectively. First, we use the simple imputer class from scikit-learn to address any gaps in our dataset. In this example, the imputer is configured to replace missing values with the mean of the corresponding feature's values. By applying the imputer to the specified feature with missing values, we ensure that our dataset remains complete, which is crucial for model accuracy. Next, we proceed with feature scaling using the standard scaler. This scaler standardizes our features by removing the mean and scaling to unit variance. Specifically, it transforms the specified features to have a mean of 0 and a standard deviation of 1, helping improve the convergence of various algorithms during training. In machine learning, scaling is essential, particularly when dealing with algorithms sensitive to the scale of input data. By following these steps, we enhance the predictability of our models while eliminating potential biases introduced by outliers or varying feature distributions. Now let's implement a new feature to enhance our dataset's predictive capabilities. In this case, we'll be creating a debt-to-income ratio, which is a crucial metric in financial analysis, particularly in evaluating an individual's financial health. To accomplish this, we'll divide the total debt by the annual income. By assigning this calculation to a new column in our data frame, we can easily track how much debt a person carries in relation to their income. This derived feature can substantially improve our model's accuracy as it captures a significant relationship that could influence our target variable. The expression df debt to income equals df total debt / df annual income essentially creates a new column named debt to income in our data frame, df. Within this column, each entry is the result of the corresponding total debt entry divided by the respective annual income for that individual. By including this new feature in our dataset, we allow our machine learning model to identify patterns related to debt levels in relation to income, potentially leading to better predictions regarding financial behavior. This illustrates the core principle of feature engineering, transforming existing data into a more informative format for modeling. Now let's see how we can implement cross-validation to evaluate model performance. First, we use the train test split function from scikit-learn to divide our dataset into training and testing sets, ensuring that 20% of the data is reserved for testing. This allows us to train our model on one portion of the data and validate it on an unseen section. Next, we initialize a logistic regression model, a common choice for classification tasks due to its simplicity and efficiency. Once the model is set up, we proceed to assess its performance using cross-validation. The cross-val score function will evaluate the model's accuracy by partitioning the training data into 5 folds. This means that the model will be trained and validated 5 times, each time using a different fold as the validation set, while the remaining folds are used for training. Finally, we print the cross-validated scores, which provide insight into how well our model is likely to perform on new, unseen data. This approach helps ensure that our model generalizes effectively and aids in comparing different algorithms down the line. Now let's see how we can implement hyperparameter tuning using Grid Search CV to optimize our model performance. In this snippet, we begin by defining a parameter grid that contains different values for the hyperparameters we want to test. Here, we're experimenting with the regularization strength parameter, C, and the algorithm, solver, for the logistic regression model. By setting up a range of values for each parameter, we allow the Grid Search CV method to explore all possible combinations systematically. Next, we instantiate the Grid Search CV object, passing in our logistic regression model, the parameter grid, and defining the number of cross-validation folds with the CV argument. This step is crucial as it enables the model to be evaluated on multiple subsets of the data, providing a more reliable estimate of its performance. Once we have prepared Grid Search CV, we fit it to our training data. This process includes training the model with different combinations of hyperparameters and assessing their performance through the defined cross-validation method. Finally, we print the best parameters found during the search. This method automates the optimization of hyperparameters, leading to improved accuracy in our predictions. Now let's see how we can evaluate the performance of our trained model using scikit-learn. Once we have our model ready and have made predictions on the test dataset, it's important to assess how well our model is performing. In this segment, we start by using the predict method of the model to make predictions on the unseen data represented by xtest. This will give us the predicted labels, which we will compare against the actual labels stored in ytest. Next, we use the classification report function from scikit-learn to generate a comprehensive report comprising several evaluation metrics. This report includes accuracy, precision, recall, and F1 score, all crucial for understanding how effectively the model is classifying each class within our dataset. Finally, we print the report to view these metrics, which help in determining the strengths and weaknesses of our model's performance. By analyzing these results, we can gain valuable insights that guide us in making necessary adjustments for future iterations of the model. Now let's see how we can implement SHAP to interpret our model's predictions. First, we start by importing the SHAP library, which provides tools for interpreting complex machine learning models. Next, we create a SHAP explainer. This explainer takes the trained model and training dataset as inputs, enabling it to understand how each feature contributes to the output predictions. After initializing the explainer, we calculate the SHAP values for our test dataset. These values represent the contribution of each feature for each prediction, highlighting which features have the most significant impact. Finally, we visualize the feature importance using a summary plot. This visualization helps us better understand the model's behavior by illustrating how each feature influences the predictions across the dataset. By analyzing these insights, we can foster transparency and trust in our model's results, which is especially crucial in sensitive domains like healthcare and finance, where stakeholders need to comprehend and trust the underlying decision-making process. Finally, after implementing your model in production, continuous monitoring is essential. Machine learning models may degrade in performance over time due to changing data distributions, also known as model drift. Setting up monitoring tools to track performance metrics can help you identify when retraining or model updates are necessary. Automated retraining pipelines can be designed to keep your model up to date and relevant. To summarize, we have covered key best practices for implementing machine learning, including defining the problem, conducting exploratory data analysis, preprocessing data, performing feature engineering, selecting models, tuning hyperparameters, validating performance, enhancing interpretability, and monitoring post-implementation. By following these best practices, you can implement machine learning solutions that are not only effective but also robust and scalable. As the field of machine learning continues to evolve, staying informed about the latest techniques and tools will ensure your solutions remain at the forefront of innovation. The journey may be challenging, but with the right practices in place, you can harness the full potential of machine learning to drive meaningful results. Now let's see how we can implement a random forest model using scikit-learn. First, we begin by loading our dataset, which is crucial for any machine learning task. The load data function will be your custom data loading logic to bring in the features and labels. After loading the data, we split it into training and testing sets using train test split, reserving 20% of the data for testing while maintaining the random state for reproducibility. Next, we create an instance of the random forest classifier with 100 trees, initializing it with a fixed random state to ensure consistent results across different runs. We then fit this model to our training data, allowing it to learn from the inputs. After training, we move on to predictions. We use the model to predict outcomes on the test set. Finally, we evaluate the model's performance by calculating the accuracy score, which tells us the proportion of correct predictions made by the model. This straightforward implementation showcases how ensemble methods like random forest can enhance predictive performance, making it a valuable tool in your machine learning arsenal. Now let's implement the AdaBoost classifier using a decision tree as the base estimator. We begin by importing the necessary libraries from scikit-learn, specifically the AdaBoost classifier and decision tree classifier. The base classifier we choose is a decision tree with a maximum depth of 1, which allows us to create a weak learner. Next, we initialize the AdaBoost model by passing the base decision tree classifier to it while specifying the number of estimators, which in this case is set to 50. This means that the model will iteratively train 50 weak learners, each focusing on the mistakes made by the previous ones. Once the model is set up, we fit it to our training data, allowing it to learn the patterns and relationships present. After training, we can make predictions using the model on our test dataset. Finally, we compute the accuracy of the model by comparing the predicted values to the actual labels in the test set. This implementation demonstrates how boosting can enhance performance by incrementally improving upon weak learners, turning them into a robust predictive model. Now let's see how we can implement hyperparameter tuning using grid search for our random forest model. First, we set up a parameter grid that defines the hyperparameters we want to test, including the number of estimators, maximum tree depth, and minimum samples required to split an internal node. This grid will allow us to explore various combinations of these settings methodically. Next, we initialize the grid search CV object with our random forest model as the estimator. We also specify the scoring metric, which in this case is accuracy, and set the number of cross-validation folds to 5. This setup enables the model to evaluate each hyperparameter combination robustly. After configuring the grid search, we fit it to our training data. This process involves training the random forest model multiple times, once for each set of hyperparameter values. Finally, we obtain the best parameters identified during this exhaustive search and print them out. This approach not only streamlines the tuning process, but also enhances the model's performance by identifying the optimal settings that could lead to significant improvements in accuracy. Now let's explore how to implement recursive feature elimination, RFE, with logistic regression in scikit-learn. First, we initialize the logistic regression model, which serves as the estimator for RFE. This model will help us identify the most significant features in our dataset. Next, we set up the RFE selector with the end features to select parameter set to 5, indicating that we want to retain only the top 5 features. By fitting the selector on our training data, RFE will systematically evaluate the importance of each feature based on the performance of the logistic regression model and remove those that don't contribute meaningfully to predictions. After executing this, we access the support attribute of the selector to obtain a mask that highlights the selected features. This step is crucial for improving model interpretability and preventing overfitting by focusing only on the most relevant data attributes, setting the stage for enhanced predictive modeling. Next, we turn our attention to principal component analysis, PCA, a technique for dimensionality reduction that simplifies our data while retaining its most informative aspects. Here, we initialize PCA with 2 components, which means we aim to reduce our dataset to 2 dimensions. By fitting and transforming our dataset, PCA compresses the original features into fewer components that still capture key variants. Finally, we print the original and reduced shapes of the dataset, which allows us to visualize the extent of data compression and understand how much information has been preserved in this transformation process. Now let's implement a learning rate scheduler, an essential tool for optimizing the training of neural networks. First, we import the learning rate scheduler from TensorFlow's Keras library, which allows us to adjust the learning rate during training dynamically. We define a function named scheduler that takes the current epoch and the learning rate as inputs. If the epoch exceeds 10, the function decreases the learning rate by 10%, which helps refine the model's updates as it learns. Next, we create an instance of learning rate scheduler, passing our scheduler function as a callback. This instance will be utilized in the model training process. Lastly, when fitting our model, we can include this learning rate scheduler in the callbacks parameter. As the model trains over the specified epochs, the learning rate will be adjusted according to our defined schedule. This method enhances convergence rates and can lead to more accurate model performance during the later stages of training, allowing for fine-tuning that helps in achieving optimal weights. Now let's implement the stacking model using scikit-learn's stacking classifier. We begin by defining our base learners, which include a random forest classifier and a support vector machine, SVM. The random forest is trained with 100 decision trees, and we set the SVM to output class probabilities, essential for the stacking process. Next, we specify a logistic regression model to serve as our meta-learner, which will combine the predictions from our base models. This step is crucial, as the meta-learner takes inputs from the predictions of the base learners to generate the final predictions. Once we have defined our models, we create an instance of the stacking classifier by passing the base learners and specifying the meta-learner. After constructing the stacking model, we fit it to our training data to learn from the various models. Finally, we evaluate our model using the test set. The predictions generated by the stacking model are compared against the actual outcomes, and we calculate the accuracy score. This technique of leveraging the strengths of multiple models is powerful, often leading to improved performance by capturing diverse relationships within the data. In summary, we have covered several advanced techniques for optimizing machine learning models that can significantly enhance performance. We explored ensemble methods such as bagging and boosting, hyperparameter tuning with grid search, feature selection techniques, and dimensionality reduction with PCA. Additionally, we discussed learning rate schedulers for improving convergence in neural networks and the powerful stacking method for combining multiple model predictions. These techniques are essential in the machine learning toolkit, enabling you to build models that are not only more accurate but also robust to changes in data. As you apply these advanced strategies, remember that the landscape of machine learning is always evolving, and staying informed will give you the edge needed to tackle the most complex problems in the field. Happy learning, and may your models be ever optimized. Now let's see how we can implement transfer learning using TensorFlow's Keras API with the MobileNet v2 model. First, we load the pre-trained MobileNet v2 model without its top layer. This configuration allows us to leverage the model's previously learned features while customizing it for our specific task. After obtaining the output from the base model, we add new layers tailored to our needs. A global average pooling to D layer that reduces the spatial dimensions of the feature maps, followed by a dense layer with 1024 units and Ray-LU activation for introducing nonlinearity. Finally, we prepare our output layer, which consists of another dense layer using the softmax activation function to predict probabilities for each class, assuming we have 10 distinct classes in our dataset. By defining the inputs and outputs, we create a new model combining the base MobileNet v2 and our custom layers. To finalize our architecture, we compile the model, specifying the atom optimizer and categorical cross-entropy as our loss function, along with accuracy as our evaluation metric. This setup is efficient as it significantly reduces training time and enhances model performance, making it particularly effective in scenarios with limited labeled data. Now let's see how we can implement AutoML using the AutoSclearn library for a regression task. First, we begin by loading the California housing dataset, which provides various features related to housing prices in California. This dataset will serve as our input for training and testing our predictive model. We then split the data into training and testing sets, keeping 20% of the data for testing. This is crucial for evaluating how well our model performs on unseen data. Next, we initialize the AutoSclearn regressor. This step is significant because it automates the model selection process, allowing the library to try different algorithms and hyperparameters to find the best model for our task. We set the total time for the task to 120 seconds and limit the runtime for each individual model to 30 seconds. Once we have set up the regressor, we fit it with our training data. The fitting process involves training the various models on the training set, enabling the regressor to learn patterns in the data. Finally, we use our trained model to make predictions on the testing set, providing us with the output we can utilize for decision-making and analysis. Now let's see how we can implement algorithmic fairness assessment using the AIF360 library. First, we begin by importing the necessary classes from the AIF360 package, specifically binary label dataset metric and binary label dataset. The binary label dataset will allow us to create a dataset that is aware of fairness metrics, specifying the favorable and unfavorable labels, as well as identifying the columns in our data frame that represent the labels and the protected attributes. In this case, we're considering gender as our protected attribute. Next, we instantiate the dataset using our data frame, passing in the appropriate label names and indicating which attribute is protected. This step is crucial for preparing our dataset for fairness evaluation. After defining the dataset, we create an instance of binary label dataset metric, which helps us analyze disparities in the dataset based on the privileged and unprivileged groups. In our example, we define the privileged group as those who identify as male, coded as 1, and the unprivileged group as those identifying as female, coded as 0. Lastly, we compute and print the disparate impact metric to examine how different groups are affected by our model's predictions, allowing us to proactively address any bias present. Now let's implement a neural network that can analyze video input and generate descriptive text using keywords. We begin by defining two input layers, one for the video frames and another for the text descriptions. The video input is shaped to handle a sequence of frames, while the text input accommodates the sequence of word indices. Next, we utilize a convolutional neural network, CNN, to extract features from each video frame. The CNN is wrapped in a time-distributed layer, which allows us to apply the same convolutional layer to each frame of the video individually. Following the convolutional operation, we flatten the output so it can feed into subsequent layers more efficiently. For text processing, we create an embedding layer that transforms the integer-encoded text inputs into dense vectors, effectively capturing semantic relationships. This is followed by an LSTM layer that processes the sequential nature of the text data, enabling the generation of coherent sentences based on the learned context. Finally, we introduce a dense output layer activated by softmax, which predicts the probability distribution over the vocabulary for the next word in a sequence, completing our multimodal architecture that integrates video and text for enhanced understanding. Now let's implement a simple anomaly detection system using the isolation forest algorithm, which is particularly effective for identifying unusual patterns in network traffic that may signal cybersecurity threats. First, we load our dataset containing network traffic data from a CSV file. It's important to ensure that our dataset is suitable for the model we are about to create. We then initialize the isolation forest model, specifying a contamination parameter that indicates the proportion of outliers we expect in our data. In this case, we set it to 0.01, meaning we anticipate about 1% of the data points to be anomalous. Next, we fit the model to our dataset, allowing it to learn the patterns of normal behavior. With the model trained, we then use it to predict anomalies in our data. The predict method outputs an array where normal observations are labeled as 1 and anomalies are labeled as -1. To make sense of the results, we add a new column to our dataset that indicates whether each observation is an outlier. Finally, we print the entries in the dataset that have been marked as anomalies, enabling us to identify potential threats in our network traffic for further investigation. Now let's see how we can implement a spam detection classifier using scikit-learn, which showcases the practical applications of machine learning in handling real-world tasks. We begin by importing the necessary libraries, including count vectorizer to convert our text data into numerical format, multinomial NB for our naive Bayes classification model, and make pipeline to streamline our process. Next, we load our dataset containing emails, which is structured with text and label columns. To prepare our model, we set up a pipeline that first vectorizes the text data and then applies the naive Bayes classifier. This pipeline not only simplifies the workflow, but also allows us to process our data in a structured manner. After fitting the model using our training data, we can test its effectiveness by predicting labels for new email inputs. We showcase this by providing examples such as a lottery notification and an account update to observe how the model classifies these emails. This hands-on approach not only illustrates the accessibility of machine learning, but also demonstrates its real-world relevance in filtering unintended communications. In summary, the future of machine learning is incredibly promising, fueled by technological advancements, an increased focus on ethical considerations, and the boundless potential for innovation across industries. As organizations embrace automation and artificial intelligence, various sectors will experience significant transformations. By democratizing access to machine learning tools, fostering multimodal learning systems, and prioritizing ethical practices, we position ourselves to reap the benefits of these advancements while mitigating the risks they may bring. As we forge ahead, it's crucial for individuals and businesses alike to stay informed and engaged in ongoing developments within this dynamic field. The journey through machine learning continues to be filled with excitement, challenges, and opportunities to shape a better future through intelligent automation. Together, let's embrace the innovations on the horizon and carry the conversation. From a practical standpoint, implementing machine learning effectively requires adherence to best practices that ensure successful outcomes. In this session, we'll delve into advanced machine learning techniques, focusing on optimization methods, best practices, and demonstrating them through Python code using scikit-learn. So far, we learned about the evolving landscape of machine learning. We discussed advanced techniques for model optimization and the integration of AI frameworks. We also touched upon the democratization of machine learning tools and the implications for accessibility and efficiency. Now, we will cover advanced machine learning techniques, emphasizing how to systematize best practices for achieving successful deployment and results. Now let's implement hyperparameter optimization using grid search with the random forest classifier. We begin by loading the iris dataset, which provides a standard sample for classification tasks. This dataset is split into features X and target labels Y that we will use in our model. Next, we define the model by instantiating a random forest classifier. This model is powerful for handling classification tasks due to its ensemble nature, where multiple decision trees are combined to enhance accuracy and reduce overfitting. Now let's establish the parameter grid, which includes 3 hyperparameters: n estimators, max depth, and min sample split. By defining various potential values for these parameters, we allow grid search to evaluate multiple combinations to find the best configuration. Following that, we configure grid search CV with our model and parameter grid, specifying accuracy as our scoring metric and using 5-fold cross-validation to ensure robust evaluation. Once we've fitted grid search to our data, we can easily retrieve the optimal hyperparameters. Lastly, we use these best parameters to analyze the model's performance, predicting outcomes on the training data, and calculating the accuracy to assess its effectiveness. Now let's see how we can implement feature engineering using pandas to enhance our dataset of dates. We start by creating a sample dataset that contains a date column alongside some corresponding values. Once we have our data structured in a pandas date frame, the next crucial step is to convert our date strings into a proper data time format. This transformation allows us to leverage the powerful date manipulation functionalities available in pandas. After converting the date column, we proceed to extract meaningful features that can improve our model's predictive capabilities. Specifically, we add 3 new columns: day of week, month, and year. The day of week captures the day of the week with Monday as 0, helping the model understand weekly patterns, while month and year provide additional temporal context. This rich set of features can significantly enhance our machine learning model's understanding of the data, as it now has more variables to identify trends and behaviors. Finally, we print the data frame to observe the newly added features and appreciate how the dataset has been enriched for better analysis. Now let's implement lasso regression, a powerful regularization technique that helps prevent overfitting in our models. First, we begin by importing the necessary libraries, including the lasso class from scikit-learn, linear model, and the make regression function from scikit-learn, datasets. This allows us to create a synthetic dataset for demonstration purposes. Next, we generate this dataset with 100 samples and 20 features, introducing a bit of noise to mimic real-world data variability. Afterward, we instantiate the lasso regression model and set the alpha parameter to 0.1, which determines the strength of the regularization. A key aspect of lasso is its ability to shrink some coefficients to 0, effectively performing feature selection by disregarding less significant features. We then fit the model to our synthetic data using the fit method, allowing it to learn and adjust the coefficients accordingly. Finally, we retrieve and print the coefficients of the trained model. This output is crucial as it helps us identify which features have been deemed insignificant by the lasso regression, simplifying our model and enhancing interpretability. Now let's see how we can implement k-fold cross-validation using scikit-learn to validate our random forest model more effectively. In the initial steps, we load the well-known iris dataset, which provides data on various iris species based on their features. We then separate this data into features X and labels Y, setting the stage for training our model. Next, we create an instance of the random forest classifier, a robust model known for its accuracy and versatility. Once the model is configured, we proceed to perform cross-validation by leveraging the cross-val score function. This method allows us to evaluate the model's performance by splitting our dataset into 5 distinct folds. As the model trains and tests on different subsets, it generates an array of accuracy scores for each fold. Finally, we display the cross-validation scores along with the mean accuracy, which provides an overall assessment of the model's performance across different datasets. This approach helps us identify potential overfitting or underfitting issues, ensuring a more reliable evaluation of the model's robustness in real-world scenarios. Now let's implement AdaBoost with a decision tree classifier to demonstrate the power of ensemble methods. First, we import the necessary classes from the scikit-learn library, AdaBoost classifier for the boosting algorithm and decision tree classifier as our base estimator. The first step is to load the iris dataset, which serves as a well-known benchmark for classification tasks, providing features X and labels Y for our model. With the data in hand, we create a simple decision tree model as our base learner, specifying a maximum depth of 1 to keep it basic and avoid overfitting. This means our tree will be a decision stump, making a single split in the feature space. Next, we initialize the AdaBoost classifier, passing in the base model and setting the number of estimators to 100, allowing it to create multiple weak learners that will be combined to form a strong final model. After setting up the model, we fit it on our training data, enabling it to learn from the patterns in the iris dataset. Finally, we evaluate the trained AdaBoost model by making predictions on the same dataset. By using accuracy score, we can print the accuracy of our ensemble method, which often outperforms the individual base model by effectively focusing on difficult-to-classify instances. In conclusion, with the integration of advanced machine learning techniques such as hyperparameter optimization, feature engineering, model regularization, cross-validation, and ensemble methods, we can significantly enhance the performance of machine learning models. The hands-on examples in Python provided us with practical insights into how these techniques can be implemented using the scikit-learn library. Now that you have a foundational understanding of these advanced techniques, I encourage you to dive deeper into each topic and explore how they can be applied to your specific machine learning projects. Always remember that the choice of methods will largely depend on your data and the problem you are attempting to solve. Thank you for joining me in this tutorial. Keep experimenting, keep learning, and happy. Machine learning evaluation frameworks are vital to ensuring that our models function correctly and meet expectations. They're the measuring sticks by which we determine the success of our algorithms. In this lesson, we'll explore evaluation frameworks, metrics, and methodologies. So far, we learned about advanced machine learning practices, including model optimization and the importance of feature engineering. We explored techniques such as hyperparameter optimization with grid search, model regularization through methods like lasso and ridge, and the significance of cross-validation for reliable model assessment. Additionally, we discussed ensemble methods that combine multiple learning algorithms to enhance prediction accuracy. Now, we will cover the evaluation frameworks essential for understanding and improving our machine learning models. Now let's see how we can implement a random forest model using the iris dataset, a popular dataset for classification tasks in machine learning. First, we load the iris dataset, which contains features of different iris flower species, and separate the data into features X and labels Y. Next, we split the dataset into training and testing sets to evaluate the model's performance effectively, using 20% of the data for testing. Next, we'll create and train a random forest classifier, which is an ensemble method that leverages multiple decision trees to improve prediction accuracy. After fitting the model to our training data, we proceed to make predictions on the test set. Evaluating the model's performance is crucial, hence, we'll utilize scikit-learn's classification report to summarize crucial metrics such as precision, recall, F1 score, and accuracy. This report will help us assess how well our model is capturing the patterns in the data, providing insights into its strengths and weaknesses for further improvement. By analyzing this classification report, we gain a comprehensive understanding of how our random forest model performs on the iris dataset. Now let's see how we can create and visualize the confusion matrix to assess our model's performance more effectively. We start by importing the necessary libraries, Seaborn for visualization, Matplotlib for plotting, and confusion matrix from scikit-learn to compute the confusion matrix itself. Once we have our predictions and true labels from the test set, we generate the confusion matrix using the confusion matrix function, which tallies true positives, true negatives, and false negatives. Next, we set up a plot with a specified figure size to ensure clarity. By using Seaborn's heatmap function, we plot the confusion matrix with annotations, making it easy to read the numbers directly. The color map is set to blues, which helps emphasize the counts. Darker shades indicate higher values. We also label the axes, indicating actual for true class labels and predicted for the model's predictions, and add a title for context. This visualization not only provides a clear snapshot of where predictions are accurate or erroneous, but also aids in identifying specific classes the model confuses, guiding us toward adjustments to improve performance. Finally, we display the plot, offering a visual tool for further analysis. Now let's implement a simple linear regression model to evaluate its performance using essential regression metrics. First, we start by generating synthetic data suitable for regression tasks. Using the makeRegression function, we create a dataset with 100 samples and one feature, while introducing some noise to mimic real-world scenarios. Next, we divide this dataset into training and testing sets to ensure that we can evaluate our model effectively. Now let's create the linear regression model using the linear regression class. After initializing our model, we fit it to the training data, allowing it to learn the relationship between the independent and dependent variables. Once the training phase is complete, we proceed to make predictions using the test set. To evaluate the performance of our model, we calculate three important metrics: mean absolute error (MAE), mean squared error (MSE), and R-squared R2. MAE provides insight into the average prediction error, MSE emphasizes larger errors by squaring them, and R2 tells us how well the independent variable accounts for the variability in the dependent variable. Finally, we print these metrics to assess the model's performance effectively. Now let's implement a learning curve using scikit-learn to visualize the model's performance across different training sizes. To begin, we utilize the learning curve function, which helps us gather crucial insights into how well our model is learning as we increase the size of our training data. This function will compute training and cross-validation scores, providing a clearer picture of whether our model is experiencing bias or variance issues. Next, we will calculate the mean training and test scores for each training size, allowing us to visualize model performance effectively. Once we have these average values, we can plot them on a graph, making it easier to assess the learning dynamics. In the plot, we will illustrate the training score in blue and the cross-validation score in orange, giving us a straightforward comparison between how the model performs on the training set versus unseen validation data. Finally, by clearly labeling the axes and adding a title, we create a visual guide that indicates both the training size and corresponding scores. This enables us to interpret whether the model is underfitting, overfitting, or striking the right balance, thereby guiding our adjustments for optimal performance. Now let's implement the following code to conduct k-fold cross-validation, a powerful technique to assess our model's performance reliably. We start by importing the cross-val score function from the scikit-learn model selection module, which will allow us to perform the cross-validation more efficiently. Next, we create a new instance of the random forest classifier, which is a robust model suitable for many classification tasks. This model will be the subject of our evaluation. We then use cross-val score to perform the cross-validation, specifying our model in the dataset features X and target Y, along with the number of folds CV equals 5. This means the dataset will be split into 5 parts. The model is trained with 4 parts and validated on the remaining one in each iteration. The output CV scores holds the accuracy scores for each of the 5 folds, giving us insight into how well our model performs across different subsets of data. Finally, we print these scores, along with the mean score, providing a clear indication of our model's overall performance and generalizability. By employing k-fold cross-validation, we build a strong foundation for validating our model's effectiveness in various scenarios. In this lesson, we have covered various machine learning evaluation frameworks that are central to understanding model performance. From exploring classification metrics like accuracy and F1 score to investigating regression metrics such as MAE and R2, we have delved into the details crucial to effectively gauging the success of our machine learning efforts. We also tackled critical concepts like bias-variance trade-offs, learning curves, and the enduring impact of cross-validation. Understanding these evaluation tools is essential to iteratively improve our models, leading us to create models that not only perform well statistically, but also deliver real-world value. Mastering these concepts makes us better prepared to face the machine learning challenges ahead, allowing us to effectively implement advanced techniques discussed previously in practical projects. Stay curious, continue to experiment, and most importantly, have fun with your machine learning. Neural networks have truly revolutionized our approach to complex problems across various fields, especially in image and speech recognition. They leverage interconnected layers of neurons to learn from vast amounts of data, enabling sophisticated pattern recognition capabilities that outperform traditional algorithms. So far, we've learned about the significance of evaluation frameworks in machine learning, focusing on metrics for both classification and regression tasks. We explored essential metrics like accuracy, precision, recall, and F1 score for classification, as well as MAE, MSC, and R2 for regression, alongside tools like confusion matrices and learning curves. We also discussed the importance of k-fold cross-validation for validating model performance and ensuring generalizability. These concepts equip us to measure model performance effectively and lead to better model optimization and predictions. Now, we will delve into understanding neural network applications, exploring how they work and how they're utilized in real-world scenarios. Now, let's implement a simple feed-forward neural network using Keras in Python. First, we generate a dummy dataset comprising 1,000 samples with 10 features each, which simulates the input data we'll train our model on. The labels for this dataset are binary, generated using random integers. This sets up a binary classification problem. Next, we define our model as a sequential type, which is ideal for stacking layers in a linear fashion. We start by adding the first hidden layer with 32 neurons and array LU activation function, specifying that the input dimension is 10. This indicates the number of features in our input data. We then add another hidden layer, also with 32 neurons and array LU activation. Finally, we create the output layer with a single neuron and a sigmoid activation function, which outputs a probability value suitable for binary classification tasks. After defining the structure of our model, we compile it using the Atom optimizer, known for its efficiency in handling large datasets. We set the loss function to binary cross-entropy, appropriate for our binary classification problem, and include accuracy as a metric to monitor our model's performance during training. Lastly, we fit the model to our training data over 10 epochs with a batch size of 32, allowing it to learn from the data and optimize its weights accordingly. Now let's implement a convolutional neural network, CNN, for image classification using the MNIST dataset, which contains images of handwritten digits. We begin by importing necessary libraries and loading the MNIST dataset. The dataset consists of training and test sets, which we reshape to match the expected input format for CNNs. Specifically, we transform each 2D image into a 4D tensor, with dimensions representing the number of samples, height, width, and channels, ensuring that the data type is set to float 32 and normalized by dividing by 255 to scale pixel values between 0 and 1. Next, we convert the target labels into categorical format for better handling during training. This will allow the CNN to output probabilities for each digit class. Now, let's define our CNN architecture, starting with a convolutional layer that uses a set of filters to extract features from the input images. We follow this with a max pooling layer, which reduces the dimensionality of the feature maps, helping to capture the most important elements while minimizing computation. Then we flatten the output from the pooling layer and add dense layers to enable classification, concluding with an output layer that uses a softmax activation function to predict the likelihood of each digit class. Finally, we compile the model with the Atom optimizer and categorical cross-entropy loss function before fitting it to the training data, allowing the model to learn and improve its accuracy through multiple epochs of trained iterations. Now let's implement a simple LSTM model using Keras for our speech recognition task. We start by importing the LSTM layer from Keras. In this case, we define a sequential model, which allows us to stack layers linearly. The first layer we add is the LSTM layer itself, configured with 50 units. The input shape is defined with two variables, time steps and features, which represent the number of time steps in your input sequences and the number of features at each time step, respectively. Here, you will need to replace these placeholders with your actual data dimensions. Next, we add a dense layer with one output unit and a sigmoid activation function to make predictions. This setup is suitable for binary classification tasks, such as determining whether a certain speech command is present. After defining the model's architecture, we compile it using the Atom optimizer, a popular choice for its efficiency, alongside the binary cross-entropy loss function, which is commonly used for binary classification. Finally, the model is trained on our dataset using the fit method, specifying the training data, number of epochs, and batch size. This process enables the model to learn from the sequences, maintaining the necessary context to improve its predictions in speech recognition tasks. Beyond these applications, neural networks find their utility in a variety of domains. In finance, they're widely used for predicting stock prices and assessing risks, leveraging historical data to find patterns that humans might overlook. In healthcare, neural networks analyze medical images or genomics data to assist in diagnosing diseases. In the world of autonomous vehicles, they help in tasks like object detection and path planning by interpreting complex sensor data. As you can see, neural networks are versatile tools in the data science toolkit. They tackle a vast array of applications by learning from past behavior, allowing them to predict and classify new data effectively. To summarize, we've explored the structure and functioning of neural networks, recognized their various applications in the real world, specifically in image and speech recognition, and seen practical implementations using Python and Keras. Understanding these fundamentals prepares us for deeper explorations into more advanced network architectures, transfer learning, and deployment in real-world systems. In our next lesson, we will dive deeper into the mechanics of training neural networks, including techniques like transfer learning and fine-tuning of models for specific tasks to improve performance and efficiency. Get ready to strengthen your neural network. Model training frameworks are essential for ensuring smooth training and efficient deployment of machine learning models. These frameworks not only streamline the process of building and deploying algorithms, but also enhance the overall efficiency of the training process. As we advance in our exploration of machine learning, understanding the enhancements made in model training frameworks becomes crucial for anyone looking to apply these technologies effectively. So far, we learned about the structure and functionality of neural networks, emphasizing their representation of connections similar to the human brain. We examined key applications in image recognition using convolutional neural networks and speech recognition with recurrent neural networks. Practical implementations in Python and Keras highlighted their effectiveness while discussing real-world applications across various domains. In this lesson, we will delve deep into advancements in model training frameworks, focusing on their architecture, features, and the latest innovations that empower modern machine learning applications. Now let's see how we can implement a simple linear regression model using scikit-learn to predict house prices based on various features. We begin by importing essential libraries, such as NumPy and Pandas for data manipulation, and specific classes from scikit-learn for model training. Next, we create a sample dataset that includes the number of rooms, total area, and respective prices of houses, which we then convert into a Pandas data frame for easier handling. After preparing our dataset, we define the features x and the target variable y for our model. The subsequent step involves splitting the dataset into training and testing sets using the train-test-split function. This is crucial because it allows us to train the model on one portion of the data and evaluate its performance on unseen data, ensuring unbiased assessment. With the data organized, we proceed to create an instance of the linear regression model, followed by fitting the model to our training data. Once the model is trained, we can use it to make predictions on the test set. Finally, we print the predictions to see how well our model estimates house prices, demonstrating the straightforward implementation capabilities of scikit-learn in a linear regression scenario. Now let's implement the following code to build a convolutional neural network, CNN, using TensorFlow and Keras, specifically aimed at classifying handwritten digits from the MNIST dataset. We start by loading the MNIST dataset, which consists of 28x28 pixel grayscale images of handwritten digits. To prepare the dataset for our model, we reshape the training and testing images to include a channel dimension, and we normalize the pixel values by scaling them to a range of 0 to 1, which is crucial for efficient learning. Next, we define our CNN model architecture. We utilize a sequential model, adding a convolutional layer that detects patterns in the images with 32 filters, each of size 3x3, followed by a max pooling layer that downsamples the feature maps to reduce computation and prevent overfitting. After flattening the pooled output, we add two dense layers. The first is a hidden layer with 64 neurons, and the second is the output layer with 10 neurons representing the classes for digits 0 through 9, using the softmax activation function to produce probability distributions for each class. Then we compile the model, specifying the Atom optimizer, categorical cross-entropy as the loss function, and accuracy as the metric for evaluation. Finally, we train the model on the training data for 5 epochs, validating it against the test set to monitor its performance and generalization. This structure demonstrates the ease and effectiveness of building complex neural networks with TensorFlow while maintaining clarity and simplicity. Now let's implement the following code to automate hyperparameter tuning for a random forest classifier using the iris dataset. We begin by importing the necessary libraries, including NumPy, Optuna, and scikit-learn components. We first load the iris dataset, which is a well-known dataset in machine learning that comprises various features of iris flowers classified into 3 species. Next, we split the dataset into training and testing sets using the train-test-split function, which allows us to evaluate our model's performance on unseen data. We then define an objective function for Optuna, which encapsulates our hyperparameter tuning process. In this function, we use Optuna's suggestInt method to dynamically choose values for critical hyperparameters of the random forest classifier, namely the number of trees n estimators and the maximum depth of the trees. After training the model with the selected hyperparameters, the function returns the model's accuracy on the testing set as the objective to be optimized. Finally, we create an Optuna study to automate the optimization process by calling studyOptimize, which runs multiple trials to determine the best set of hyperparameters. The optimal parameters are printed out, showcasing the effectiveness of using Optuna to enhance model performance efficiently. Now let's see how we can implement a distributed training setup using Horovod with TensorFlow. We start by importing the necessary libraries, Horovod and TensorFlow. The first step is to initialize Horovod, which sets up the environment for distributed training across multiple GPUs or nodes. After that, we load the MNIST dataset, performing preprocessing to reshape the images and normalize them to a range suitable for training. Next, we define the convolutional neural network model architecture using TensorFlow SCIKIT's API. This model consists of convolutional layers followed by max pooling, flattening the output in 2 dense layers. Importantly, we modify the optimizer to be distributed by wrapping the Atom optimizer with Horovod distributed optimizer, allowing gradients to be averaged across all participating GPUs during training. Finally, we compile and fit the model, specifying the loss function and the metrics to monitor during training. We also include a callback to synchronize global variables after each epoch. This setup leverages the power of distributed computing, enabling faster training times and the ability to tackle larger datasets or more complex models efficiently. Through our discussion, we see that model training frameworks have evolved significantly, bringing a wealth of capabilities to the table. Frameworks like scikit-learn, TensorFlow, and PyTorch provide powerful, user-friendly interfaces for building models, while tools like Optuna enhance their efficiencies through automated parameter tuning. Moreover, with distributed training advancements, we are now in a position to scale our models seamlessly to accommodate growing datasets and increasing complexity. As we move forward, one of the most critical skills to develop is how to select and optimize the right frameworks for your specific data science objectives. Not only does this choice impact performance and accuracy, but it also influences the overall project timeline and resource allocation. In the next lesson, we will expand on these concepts by diving into advanced techniques for training neural networks, including transfer learning and fine-tuning methods. With the knowledge gained from selecting appropriate training frameworks, you'll be well equipped to tackle these advanced strategies effectively. Let's get ready to take our understanding of model training frameworks to the next. Machine learning is not just a buzzword, it's rapidly transforming various industries with its advanced applications that showcase its power and versatility. From healthcare to finance and beyond, machine learning is becoming indispensable for solving complex problems. Today, we'll delve deeper into these advanced applications, exploring how they work and the impressive results they yield. Now let's implement the following code to create a predictive model using logistic regression, which enables us to determine the likelihood of a patient having diabetes based on various health-related features. First, we load the diabetes dataset using pandas, which allows us to handle data conveniently. We then separate the feature's input variables by dropping the outcome column while the target variable, indicating whether the patient has diabetes, is stored separately. Next, we split our dataset into training and testing sets using the train-test-split function, which helps in evaluating the model's performance on unseen data. This is crucial for avoiding overfitting and to ensure the model generalizes well. With the model initialized, we fit it to the training data, allowing the logistic regression algorithm to learn from the input features. After training, we make predictions on the test set, generating outputs that indicate predicted diabetes outcomes. Finally, we assess our model's effectiveness by calculating the accuracy score, providing insight into how well our model performs. This structured process highlights the straightforward yet powerful approach of logistic regression in medical diagnostics. Next, we will implement a random forest classifier to detect fraudulent transactions using machine learning. First, we begin by importing necessary libraries such as pandas for data manipulation and scikit-learn's random forest classifier for building our model. We then load the dataset containing credit card transactions, ensuring to separate the features from the target variable, which indicates whether a transaction is fraudulent. Now let's prepare our dataset for training by splitting it into training and testing sets. We allocate 70% of the data for training and use the remaining 30% for testing, which allows us to evaluate our model's performance on unseen data. With our data prepared, we proceed to initialize the random forest model with 100 estimators, a parameter that controls the number of trees in the forest and helps improve accuracy and robustness. Next, we fit the model using the training data, enabling it to learn from the historical patterns associated with fraud. After training, we make predictions on the test set to identify new transactions classifications. Finally, we evaluate our model's performance by generating a classification report, which provides key metrics like precision, recall, and F1 score, essential for understanding how well our model distinguishes between fraudulent and non-fraudulent transactions. Now let's see how we can implement customer segmentation using the k-means clustering algorithm. First, we start by importing the necessary libraries, including pandas for data handling, k-means from scikit-learn for the clustering functionality, and matplotlib for visualizing the results. Next, we load our dataset, which contains customer data. The focus is on two important features, purchase frequency and average order value, which we select to form the input variable x. After setting the features, we initialize the k-means model, specifying the number of clusters we want to identify, in this case, 3 distinct customer segments. With our model ready, we proceed to fit it with the data. This step allows k-means to analyze the patterns and group the customers accordingly. Once the clustering is complete, we enhance our original dataset by adding a new column for cluster labels, indicating the segment each customer belongs to. Finally, to visualize the results, we create a scatter plot displaying the clusters, with purchase frequency on the x-axis and average order value on the y-axis. This visualization helps businesses identify different customer groups, enabling tailored marketing strategies that resonate more effectively with each segment. Now let's take a look at how we can implement sentiment analysis using the NLTK library's VADER sentiment analyzer. First, we import the necessary library and initialize the sentiment analyzer. It is essential to download the VADER lexicon to ensure our analyzer has access to the required sentiment data. Following that, we define a sample list of customer reviews as our text data, which contains various expressions of sentiment towards a product. Next, we will iterate over this list of texts, applying the sentiment analyzer to each review. The polarity scores method computes a sentiment score for each text, outputting a dictionary that includes measurements of positive, negative, neutral, and compound sentiment. This compound score provides an overall sentiment rating which we will print alongside the original text. Through this process, businesses can gain valuable insights into customer sentiments, enabling them to make data-driven decisions that enhance their strategies. By analyzing the sentiment of these reviews, organizations can better understand customer opinions and improve their products or services accordingly. Now let's see how we can implement a convolutional neural network, CNN, that enables self-driving cars to process and classify images from their camera feeds. First, we import the necessary libraries, including NumPy for numerical operations and Keras for building our neural network model. Data from the training images is processed with the image data generator, which rescales pixel values to a range of 0 to 1 for better training performance. This generator is set up to read images directly from a specified directory, targeting a size of 150 x 150 pixels and using a batch size of 32 for efficiency. Next, we initialize our CNN model using Keras' sequential API, which allows us to add layers in a linear stack. The first layer is a convolutional layer with 32 filters, which helps the model learn spatial hierarchies in the images through the application of the RayLU activation function. Following the convolution, we include a max pooling layer to reduce the dimensionality of the feature maps. The resulting data is then flattened before being passed through dense layers. The first dense layer consists of 128 neurons with RayLU activation, leading to the final dense layer that outputs a single value with a sigmoid activation function, ideal for binary classification tasks. Finally, we compile the model with the atom optimizer and binary cross-entropy loss function before fitting it to our training data over 10 epochs, focusing on steps per epoch for efficient training. Through this process, the model learns to identify and classify objects in real-time driving scenarios. Machine learning's adaptability to advanced applications in various fields cannot be overstated. In finance, healthcare, marketing, and many other sectors, its potential to enhance operations, improve decision-making, and optimize results is being realized daily. As we continue our journey with machine learning, we'll examine how to refine our models further and discuss techniques that improve performance, such as transfer learning and fine-tuning methods. This discussion about advanced machine learning applications has provided a glimpse into the power and versatility of these technologies. We've explored various domains and their specific challenges, showcasing how machine learning can offer innovative solutions. As our exploration continues, we'll build on this foundation and look into the nuances of model training to achieve even better results in the field of machine learning. Now let's implement the following code to help us create a convolutional neural network, CNN, for the analysis of medical images. We begin by importing essential libraries from TensorFlow, particularly the sequential model and different layers needed to build our CNN, such as comp2D, maxPooling2D, flatten, and dense. Next, we prepare our dataset using the ImageDataGenerator class, which rescales the image pixels to a range suitable for training. We then create a training generator to load the images from the specified directory, ensuring they are correctly resized for the model. Following data preparation, we define the structure of our CNN. The model comprises convolutional layers that extract features from the images, followed by maxPooling layers that help reduce dimensionality and prevent overfitting. We simplify the output with a dense layer that predicts whether the image indicates a healthy or unhealthy condition, utilizing a sigmoid activation function for binary classification. Finally, we compile the model with the atom optimizer and binary cross-entropy as the loss function. This makes our CNN ready for training, and we execute it on our training data to observe how effectively the model learns to distinguish between healthy and unhealthy images. Now let's see how we can implement a simple fraud detection model using logistic regression, which is effective for classifying transactions as either legitimate or fraudulent. First, we begin by loading our transaction dataset from a CSV file using pandas. This dataset contains essential transaction features such as the amount, location, and user behavior score, which we will use as inputs to our model. Next, we prepare our features and labels, where the features \x_ consist of the relevant columns from the data, while the labels \y_ indicate whether each transaction is fraudulent or not. To ensure our model generalizes well, we split the dataset into training and testing sets, allocating 20% of the data for testing purposes. Now let's implement the logistic regression model, which we create and fit to the training data. This model learns to identify patterns in the data, helping it classify unseen transactions based on previous training. Finally, we evaluate the model's performance by calculating its accuracy on the test set, providing insights into how effectively it can detect fraudulent activities in real time, thereby enhancing the security of financial transactions. Now let's see how we can implement k-means clustering to analyze customer segments based on their annual income and spending behaviors. First, we begin by loading the customer data from a CSV file, which contains relevant features for our clustering analysis. We specifically select the features of age, annual income, and spending score from the dataset, as these attributes will allow us to identify patterns within spending behaviors among different customer groups. Next, we initialize the k-means algorithm, specifying that we want to create 3 distinct clusters. This choice is based on the assumption that our customer base can be categorized into 3 primary segments. We then apply the k-means algorithm to our feature set, predicting which cluster each customer belongs to and storing this information in a new column labeled cluster within our dataset. To visualize the results of our clustering, we use a scatter plot. This plot displays the relationship between annual income and spending score, with colors representing the different customer segments identified by the k-means algorithm. This visualization not only helps marketers understand their customer base better, but also aids in developing targeted marketing strategies for improved engagement and conversion rates. Now let's implement a simple sentiment analysis model using the VADER sentiment analysis library. First, we start by importing the necessary libraries, particularly NLTK and the Sentiment Intensity Analyzer from the NLTK Sentiment Veda module. We create a list of sample customer reviews which will be analyzed for sentiment. These reviews range from positive to negative sentiments, illustrating a variety of customer experiences. Next, we initialize the Sentiment Analyzer by downloading the VADER lexicon, which is essential for the sentiment calculations. With the analyzer ready, we proceed to loop through each review in our list. For every review, we calculate its sentiment score using the polarity scores method of the analyzer. This method generates a score that quantifies the sentiment in terms of positive, negative, and neutral values, along with a compound score which provides an overall sentiment measure. Finally, we print each review alongside its corresponding sentiment score. This process not only helps assess customer sentiments quickly, but also allows businesses to glean insights into customer feedback effectively, enabling them to address concerns promptly and enhance satisfaction. Now let's see how we can implement a linear regression model to predict future stock prices based on past price trends. We start by importing the necessary libraries, such as pandas for data manipulation, the train test split function from sklearn to split our dataset, and linear regression for our modeling. After loading the stock price data from a CSV file, we prepare our features and labels by selecting the previous prices as input X and the current prices as output Y. Next, we split our dataset into training and test sets to evaluate the model's performance later. With a test size of 20%, we ensure that we have a separate portion of data to gauge how well our model can predict unseen stock prices. Now we train our linear regression model using the training data, which involves fitting the model to the relationship between previous and current prices. Once our model is trained, we shift to making predictions by applying it to the test set. Finally, we visualize our predictions against the actual prices using a scatter plot, with real prices in blue and predicted prices in red. This visual representation helps us assess how closely our model's predictions align with reality, illustrating the power of predictive analytics in stock price forecasting. Now let's see how we can implement a simple maze environment for an agent using reinforcement learning techniques. We start by defining the maze_env class, which initializes a maze of a specified size, setting the starting point at the top left corner and the goal point at the bottom right corner. The step method processes the agent's movements based on the given actions, up, down, left, or right, carefully checking the boundaries of the maze to ensure the agent doesn't move outside the defined space. This method returns the agent's new state after each move. Next, we create an instance of the maze with a size of 5. This provides a manageable space for the agent to navigate. To simulate the agent's decision-making, a series of actions is executed in a loop, demonstrating how the agent interacts with the maze. Each action updates the agent's position and allows us to observe the effect of its movements as extracted through print statements. This simple representation lays the groundwork for understanding how an agent can learn to find the optimal path through exploration and reinforcement learning. Now let's see how we can implement a fairness evaluation in our classification model. We begin by creating a synthetic dataset using the makeClassification function, which generates a balanced dataset with samples suitable for binary classification tasks. This dataset will help us assess how our model performs across different demographic groups. Next, we split the dataset into training and testing subsets, ensuring that our model can learn from one part while being validated on another. We then proceed to train a logistic regression classifier with the training data, a method that is straightforward yet effective for classification problems. Now let's evaluate the model's accuracy across different groups in our dataset, specifically focusing on a feature that delineates those groups. By applying conditional predictions based on this feature, we calculate the accuracy for 2 distinct groups. This approach allows us to see if our model is biased towards one group over another. Finally, we print the accuracy results for both groups, which provides insight into how equitably the model performs and reinforces the importance of fairness in AI applications. In conclusion, we're witnessing an exhilarating evolution in artificial intelligence that influences various sectors. From redefining healthcare diagnostics and enhancing financial security to paving the way for personalized marketing and autonomous systems, AI is pushing the boundaries of what is possible. However, as we embrace these trends, we must also prioritize ethical considerations to ensure AI serves humanity positively and equitably. The journey of exploring AI is far from over. It is merely the beginning. Keep your curiosity alive as we delve into future discussions on more advanced techniques and innovations that lie on the horizon. Together, we will embrace the tech of tomorrow and build a better world. Performance metrics play a critical role in evaluating the effectiveness of machine learning models. They provide invaluable insights into how well a model performs, allowing us to make informed decisions about its usability and effectiveness in real-world applications. Today, we will explore various advanced machine learning performance metrics, focusing on their importance, implementation, and interpretation. By the end of our session, you will be equipped to select appropriate metrics for different machine learning problems and understand their implications. So far, we learned that artificial intelligence is rapidly transforming various industries, including healthcare, finance, and marketing, with significant advancements in machine learning applications. We've explored techniques such as predictive modeling for diagnostics, fraud detection, personalized marketing through customer segmentation, and natural language processing for sentiment analysis. Additionally, we discussed the importance of ethical considerations in AI development to ensure fairness and accountability. As we continue our journey, we will delve deeper into emerging AI trends and technologies that shape our future. Now, we will cover advanced performance metrics that will help you evaluate machine learning models more effectively. Now let's implement the following code to calculate precision, recall, and F1 score using Python's scikit-learn library. First, we import the necessary metric functions, precision score, recall score, and F1 score from scikit-learn metrics. These functions will help us evaluate the performance of our classification model based on the predictions it makes. We then define two lists, whitetrue, which represents the actual true labels of the instances, and whiteBread, which contains the model's predicted labels. These lists will serve as the foundation for our metric calculations. By passing whitetrue and whiteBread into the functions for precision, recall, and F1 score, we can obtain their respective values, which encapsulate critical aspects of our model's performance. Finally, we print out the calculated scores with formatted output for clarity. Each score provides us insights into how well our model is identifying true positives in relation to false positives and false negatives. Understanding these metrics is essential, particularly in scenarios of uneven class distribution, as they give a more comprehensive view of a model's effectiveness beyond mere accuracy. Now let's implement the code to calculate the ROC-AUC score, which is crucial for understanding our model's performance in classification tasks. First, we begin by importing the ROC-AUC score function from the scikit-learn metrics module. This function is designed to compute the ROC-AUC score, allowing us to evaluate how well our classifier distinguishes between positive and negative classes based on predicted probabilities. Next, we define yproba, a list that contains the predicted probabilities of the positive class for each instance in our dataset. This is critical because the ROC-AUC score relies on these probabilities rather than class labels, as it measures the ability of the model to discriminate across various threshold levels. We then need to ensure we have the actual true labels stored in whitetrue to compare against our predicted probabilities. Following that, we simply call ROC-AUC score, passing in whitetrue and yproba as arguments. This function computes the ROC-AUC score and assigns it to the variable ROC-AUC. Finally, we print the ROC-AUC score formatted to 2 decimal places, which gives us a concise view of our model's discriminatory power. This metric is especially valuable as it encapsulates the model's performance across multiple classification thresholds, providing deeper insights beyond simple accuracy. Now let's implement the calculation of mean absolute error, MAE, and mean squared error, MSE, two critical metrics used to evaluate the performance of regression models. We begin by importing the necessary functions from the scikit-learn library, which provides a straightforward approach to calculate these metrics. In our example, we define two lists, one for the actual values, yactual, and the other for the predicted values, ypredicted. These lists contain numbers representing the observed and model-predicted outcomes, respectively. With these values established, we proceed to calculate MAE and MSE using scikit-learn's built-in functions. MAE will give us the average of the absolute differences between predicted and actual values, offering an intuitive understanding of how far off our predictions are. Conversely, MSE will provide a measure that squares these differences before averaging them, thus placing greater emphasis on larger errors. After the calculations, we print both metrics formatted to 2 decimal places, allowing us to easily interpret the results. This implementation not only aids in understanding model accuracy, but also highlights the implications of prediction errors in practical applications. Now let's see how we can compute the R-squared score, which is essential for evaluating the performance of regression models. First, we import the R2 score function from the SCIKIT metrics module. This function will allow us to calculate how well our model predicts the variance in the dependent variable based on the independent variables. To perform the calculation, we need two sets of data: y-actual, which contains the true values, and y-predicted, which holds the predictions made by our model. Once we have our actual and predicted values, we call the R2 score function, passing in these two datasets. The result, stored in the variable R2, represents the proportion of variance in the outcome that can be explained by the model's inputs, indicating how well our model fits the data. Finally, we print out the R-squared score in a formatted manner, showing it to 2 decimal places for clarity. This score, ranging from 0 to 1, provides an intuitive measure of model performance, highlighting how effectively the model captures the variability inherent in the dataset. However, it's crucial to keep in mind that R2 alone doesn't determine if the model is good. We must consider other metrics for a complete evaluation. Now let's implement a multi-class classification report using the classification report function from scikit-learn. We start by defining 2 lists, one for the true labels, yTrueMulti, and another for the predicted labels, yPredMulti. In this scenario, we have 3 classes represented by integers 0, 1, and 2. The classification report function generates a detailed report of various classification metrics, which we then store in a variable called report with the parameter output_dict equals true for easier data access. Next, we focus on the macro-averaged metrics, which are particularly helpful in understanding model performance across all classes, especially in imbalanced datasets. We extract the macro precision, recall, and F1 score from the report. Each of these metrics provides significant insight into how well the model is performing. Precision shows the accuracy of the positive predictions, recall indicates how well the model captures all positive instances, and the F1 score represents the balance between precision and recall. Finally, we print these macro-averaged metrics, giving us a concise summary of the classifier's effectiveness in handling multi-class classification tasks. Now let's see how we can implement feature importance using a random forest model. We begin by importing the necessary library, Random Forest Classifier, from scikit-learn Ensemble, which provides us with the random forest algorithm, along with NumPy for numerical operations. Next, we define a sample dataset, X, consisting of input features and the corresponding target variable, Y. This dataset is a basic binary classification example with a few data points. Once we have our data ready, we create an instance of the random forest classifier and fit our model to the data using the fit method. This step essentially trains the model, enabling it to learn the underlying patterns in the data. After training, we extract the feature importances by accessing the feature importances attribute of the model. This attribute provides a numerical score for each feature, indicating its contribution to the model's predictions. Finally, we print out the feature importances to understand which features are most influential in driving the model's decisions. By analyzing these importances, we can refine our feature selection and improve the model's performance further. Lastly, selecting the right performance metric can significantly impact the decision-making process for deploying machine learning models. Contextual factors, such as the business implications of false positives versus false negatives, must inform your choice of metrics to align with desired outcomes. For instance, in medical diagnostics, false negatives might be more detrimental than false positives, guiding practitioners to prioritize recall over precision. In conclusion, the world of performance metrics in machine learning is rich and diverse, enabling practitioners to closely assess models tailored to specific tasks. By leveraging metrics like precision, recall, F1 score, AUC-ROC, and regression-specific metrics like MAE and R2, you gain a comprehensive understanding of your model's accuracy and reliability. As we wrap up, we've covered various advanced performance metrics crucial for evaluating machine learning models. The ability to choose and interpret these metrics effectively provides a foundation for building successful machine learning applications. Remember, understanding the nuances of these metrics allows you to better grasp model performance and make informed decisions in deploying them in real-world scenarios. Data visualization methods are essential for interpreting complex datasets and model outputs. With the increasing complexity of data in machine learning projects, the need for effective visualization techniques has never been more critical. Visualization acts as a bridge, allowing us to convey insights derived from data and model performance in an understandable manner. Today, we will delve into advanced data visualization techniques that not only highlight key patterns in our data, but also enhance our ability to communicate findings effectively. So far, we learned that performance metrics are essential for evaluating machine learning models, providing insights into their effectiveness and guiding decisions for real-world applications. We've explored classification and regression metrics, including accuracy, precision, recall, and R2, emphasizing their implementation and interpretation. Additionally, we discussed the significance of application-specific metrics and feature importance in model evaluation. As we proceed, we will deepen our understanding of advanced data visualization techniques and their implications for interpreting machine learning results. Next, we will write the following code to create a simple bar chart to compare the accuracy of 3 different machine learning models. We start by importing the matplotlib library, which is essential for creating a variety of visualizations in Python. Then, we define our data, the model's names, and their corresponding accuracy scores. Here, Model A, Model B, and Model C are used with accuracy values of 0.85, 0.9, and 0.78 respectively. Now let's implement the bar function to create vertical bars for each model, giving them distinct colors for better visibility. To ensure our graph is more informative, we set the y-axis limits to range from 0 to 1 using ilim, which accommodates the accuracy scale. We also provide a title for clarity, labeling it Model Accuracy Comparison, and specify the axes labels to indicate what the graph represents. Finally, we use show to display the chart. This visualization effectively illustrates the performance of different models, helping us quickly identify which one performed the best based on accuracy. Simple visualizations like this are fundamental for understanding model evaluations. Next, we will explore how to visualize the distribution of prediction errors using a box plot. First, we import the necessary libraries, Seaborn for visualization and NumPy for handling numerical data. To generate some sample prediction errors, we set a random seed for reproducibility and create an array of random errors drawn from a normal distribution with a specified size of 100. Now let's implement the box plot using Seaborn's boxplot function, which takes our array of errors as input. This function will automatically calculate the median, quartiles, and identify any potential outliers in the data. To enhance our visualization, we add a title that describes the plot as box plot of prediction errors and label the y-axis as error for clarity. Finally, we call plt show to display the box plot. This visualization effectively illustrates the spread and key characteristics of the prediction errors, allowing us to assess model performance at a glance. By analyzing the box plot, we can identify whether there are any outliers that warrant further investigation into the underlying dataset or model assumptions. Now that we are ready to explore scatter plots, let's see how we can implement a visualization to uncover the relationship between 2 continuous features. We begin by importing the necessary libraries, including pandas for data manipulation and matplotlib's pyplot along with Seaborn for our visualization needs. Next, we create a sample dataset with 2 features, Feature 1 and Feature 2, generated using NumPy's random uniform function to simulate continuous variables. Additionally, we include a target variable taking on categorical values R and B, which will be used to color code our scatter plot, enabling us to distinguish between different classes. Now let's take a look at how to set up the visualization. We establish a figure size for clarity, then use Seaborn's scatterplot function to plot Feature 1 against Feature 2. The hue and style parameters allow us to differentiate points based on the target variable, enhancing interpretability. Finally, we add titles and axis labels for context, display a legend for clarity, and call plt show to render the plot. This scatter plot will help us visually assess any patterns or separations between the classes, which can be crucial for effective classification. Now let's implement the following code to create an interactive scatter plot using Plotly. First, we start by importing the necessary library, Plotly Express, which simplifies the creation of complex visualizations. We then define our scatter plot by calling the px_scatter function, where we specify our data frame, df, along with the x and y coordinates that represent the features we wish to plot, Feature 1 and Feature 2. Additionally, we use the color argument to distinguish points based on their categorical target variable, which enhances our ability to visually assess the relationships and patterns within the data. The title parameter adds a descriptive title to the plot, making it clear what the visualization represents. Finally, we call figshow to display the interactive scatter plot. This interactive feature allows users to hover over each data point to reveal detailed information, which significantly enriches user engagement and facilitates deeper exploration of the dataset. By leveraging Plotly's capabilities, we make our visualizations not just informative but also engaging, perfect for presentations and collaborative environments. Now let's see how we can visualize feature importance using the random forest algorithm in our analysis. First, we begin by importing the necessary libraries, specifically scikit-learn's datasets and the random forest classifier, which will allow us to construct our model. We then load the iris dataset, a classic dataset used for classification tasks, and separate it into feature data X and target labels Y. Next, we fit a random forest classifier to our dataset, an ensemble method known for its robustness and effectiveness in capturing complex relationships between features and labels. Once the model is trained, we can access the feature importances that the model has learned, which quantify the contribution of each feature in making predictions. Now let's implement the visualization of these importances. After retrieving the importance values, we sort them in descending order to highlight the most significant features. We'll then use matplotlib to create a bar chart where each bar represents the importance of a feature, making it easy to compare them at a glance. This visualization enhances our understanding of which features are driving our predictions, guiding our considerations for feature selection and model refinement moving forward. Now let's see how we can implement a confusion matrix to evaluate our classification model's performance. We begin by importing the necessary library, confusion matrix from scikit-learn, which computes the confusion matrix based on the true and predicted labels. For this example, we define a set of sample true labels, white true, and their corresponding predictions, white red. The confusion matrix function takes these inputs and calculates the matrix, which provides insights into the model's prediction accuracy by categorizing outcomes into true positives, true negatives, false positives, and false negatives. Next, we will utilize Seaborn to create a visually appealing heat map that represents this confusion matrix. We set the figure size to ensure clarity and use the heat map function to plot the confusion matrix using a blue color palette. The anode equals true parameter allows us to display the numerical values within the respective cells, enhancing interpretability. We also add descriptive labels for the X and Y axes, specifying the predicted and true labels. Finally, we employ PLT show to render the heat map, facilitating an easy visual assessment of the model's classification performance and where it may be misclassifying predictions. So far, we have covered a variety of advanced visualization techniques, from basic bar charts and box plots to interactive scatter plots and confusion matrices. Each technique serves a purpose in enhancing our understanding of the data and model results. By continuing to integrate these visual tools, you can not only improve your workflow, but also increase your ability to share insights and communicate findings effectively. As we approach the conclusion of our session, let's briefly summarize the key points. Advanced data visualization techniques are essential for interpreting complex datasets and model outputs. By harnessing libraries like matplotlib, Seaborn, and Plotly, you can create a range of visualizations that effectively communicate insights. Whether you're comparing model performances, exploring data distributions, or analyzing feature importance, these visual tools will empower you to make informed decisions in your machine learning projects. Implementing these techniques into your workflow can transform your analysis from mere numbers and metrics into actionable insights that can directly influence model development and decision-making processes in real-world applications. Keep experimenting with these libraries and visualizations to enhance your data storytelling skills and keep your audience engaged. Thank you for joining this session, and I look forward to our next discussion on optimizing machine learning work. Effective data processing is fundamental to the success of machine learning implementations. Today, we're diving deep into the realm of advanced data processing techniques that will not only enhance your data handling skills, but also empower your machine learning models to achieve better performance. We'll explore various advanced methodologies including data cleaning, transformation, scaling, and integration, utilizing Python libraries such as pandas and scikit-learn. Now let's take a look at how we can handle missing values in our dataset using the pandas library. We start by creating a sample data frame with some missing entries in columns A and B. To assess the extent of these missing values, we utilize the isNull method in conjunction with the sum function, which tallies the number of null entries in each column. This step is vital as it allows us to identify the columns that need attention. Next, we implement strategies to fill in these missing values. For column A, we choose to replace its missing value with the mean of the column, thereby maintaining the statistical integrity of the data. For column B, we opt for a forward fill method, which fills the missing value with the last valid observation. This approach preserves the sequential nature of the data and ensures continuity in the observations. After applying these techniques, we print the updated data frame, demonstrating how effective handling of missing values can enhance the quality of our data and prepare it for more in-depth analysis. Now let's implement the following code to transform our dataset by one-hot encoding the city variable. We begin by creating a simple data frame that contains sales data associated with different cities. This initial setup allows us to illustrate how categorical variables can be converted into a format suitable for machine learning models. Next, we utilize the pandas getDummies method, which effectively converts the categorical variable city into multiple binary columns, one for each unique city in the dataset. This transformation alters our original data frame, replacing the single city column with 3 new columns that denote whether each row corresponds to New York, Los Angeles, or San Francisco. This method is crucial for machine learning as it enables models to process categorical information numerically. By transforming categorical features into a binary format, we enhance the model's ability to interpret the data, ultimately improving its performance during training and predictions. Thus, with this operation, we set ourselves up to leverage valuable categorical information effectively in our analyses and modeling processes. Now let's see how we can implement scaling techniques using scikit-learn. We start by importing the necessary scalars, standard scalar and min-max scalar, from the sklearn preprocessing module. Next, we create a simple data frame with 2 features, feature 1 and feature 2, containing some sample numerical data. This setup allows us to clearly see the impact of each scaling method. The first scaling technique we apply is standard scalar. This method standardizes the dataset by removing the mean and scaling to unit variance, which helps ensure that the features contribute equally to the modeling process. After fitting the scalar to our data frame, we transform the data and print the results, showcasing how the values have been adjusted to have a mean of 0 and a standard deviation of 1. This is particularly useful when working with algorithms sensitive to the scale of the input data. Next, we implement min-max scalar, which scales the data to a fixed range, typically between 0 and 1. This transformation is beneficial when the model requires proportions, allowing for an effective comparison between features. Similar to before, we fit this scalar to our data frame and print the transformed data, offering a clear view of how the scaling affects the original values. Understanding these scaling methods is essential for optimizing your machine learning models. Now let's see how we can implement feature selection using recursive feature elimination, RFE, with the iris dataset. We begin by loading the well-known iris dataset, which contains measurements of different iris flowers along with their species labels. After loading the dataset, we separate the features X from the target labels Y, which allows us to prepare the data for modeling. Next, we create a logistic regression model, which will be used as the estimator in RFE. The logistic regression model is chosen due to its widespread application in binary classification tasks. Now, we will use RFE to identify the top 2 most significant features that contribute to the model's predictions. By initializing RFE with our model and specifying the number of features we want to retain, we allow RFE to recursively eliminate the least important features. Once we fit the RFE model to our data, we can access the fit-support array, which indicates which features have been selected, and the fit ranking, which shows the ranking of each feature's importance. This systematic approach not only streamlines our model by focusing on essential features, but also enhances interpretability, yielding clearer insights into which features drive predictions. Now let's see how we can implement data aggregation using pandas by merging 2 datasets. In our example, we first create 2 dictionaries, Data 1 and Data 2, which represent 2 different sets of information regarding students. The first dataset contains student names alongside their unique student IDs, while the second dataset provides the corresponding grades for these students. Next, we transform these dictionaries into pandas data frames, DF1 and DF2. These data frames serve as the foundation for our merging operation. We then use the PD-merge function to combine these 2 data frames based on the common key, student ID. This merging process effectively joins the information contained in both data frames, allowing us to analyze student performance in a more integrated manner. Finally, we print the merged DF, which reveals a cohesive dataset where each student's name is paired with their respective grade. This consolidation of data enhances our ability to perform comprehensive analyses, as all relevant information is now conveniently located within a single data frame. This technique is crucial for effective data processing, particularly when dealing with multiple sources of information. Now let's implement the following code that showcases how to perform data integration using the Dask library. First, we import the Dask data frame module, which allows us to handle large datasets that exceed our system's memory capacity. Next, we specify the location of our multiple CSV files by using a wildcard pattern in the read CSV function. This enables us to easily read in all files that fit this pattern in one go, effectively combining them into a single Dask data frame. By doing so, we facilitate the aggregation of our data. Subsequently, we perform a grouping operation on the Dask data frame, allowing us to group the data based on a specific column. In this case, we calculate the mean of each group by using the mean method, which provides insights into the average values across our groups. Importantly, we then call the compute method. This triggers the actual computation and converts the Dask data frame back into a standard pandas data frame, making it easy to work with for further analysis. Finally, we print the aggregated results, providing us with a clear output to inspect. This process illustrates how Dask can efficiently manage large datasets while enabling real-time data integration and transformation. In conclusion, effective data processing is vital for successful machine learning implementations. As we have explored, advanced techniques such as data cleaning, transformation, scaling, feature selection, data aggregation, and integration can significantly enhance our datasets, making them more suitable for analysis and modeling. Mastering these techniques not only improves data quality, but also empowers models to deliver better predictions, performance, and insights. With this knowledge, you are now equipped to tackle the complexities of data processing in your future machine learning projects. Remember, the quality of your data directly influences the efficacy of your insights and decisions. Happy coding and stay excited about the possibilities that come with. Model deployment often presents unique challenges that must be carefully managed for success. The deployment phase of a machine learning project is the bridge that connects robust model training and end-user experience. It's crucial to ensure that the model functions seamlessly in a production environment, delivering reliable predictions. In this lesson, we will explore the complexities of deploying machine learning models successfully and the pitfalls we should be wary of. So far, we covered effective data processing for machine learning, focusing on advanced techniques that enhance data quality and model performance. Now, we will dive into understanding the hurdles and challenges that come with deploying machine learning models in real-world scenarios. Now, let's see how we can implement version control for our data and models using DVC along with Git. The first command initializes a new DVC repository in your project directory, setting up the necessary configuration to start tracking your datasets and models. Subsequently, we declare the data file we want to track by using the DVC add command, which not only tracks the file, but also records its metadata in a corresponding file for DVC. Once our dataset is set up for tracking, it's important to commit these changes to Git. This is done with the git add command to stage the newly created DVC metadata file, as well as the gitignore file that DVC generates to avoid committing large data files directly into Git. The commit command then records the staged change along with a descriptive message, ensuring that your team remains informed about what has been added or changed. Next, we define a DVC pipeline stage to train our model by using the DVC run command. This command specifies the training script, the data dependency, and the output model file, allowing for an automated and reproducible training process. By executing this command, we create a seamless way to manage updates and oversee the training of our model while keeping everything properly versioned. Now let's see how we can implement model performance monitoring using the Evidently AI library. First, we begin by importing the necessary components from the library, which includes the column mapping, report, and classification performance classes. Setting up the column mapping is crucial as it defines how we align our target and prediction columns, ensuring that we are comparing the right data. Next, we construct the report by initializing an instance of the report class and specifying the metrics we wish to include. Here, we use classification performance, which provides a detailed analysis of the classification metrics. Once the report object is ready, we run it with reference data and current data to assess the model's performance over time. This step involves passing in our reference df and current df while specifying the column mapping we defined earlier. Finally, we save the generated report as an HTML file. This allows us to visualize the results and track how our model is performing against the reference data. By reviewing these reports regularly, we can identify any performance issues early and take necessary actions to maintain the model's accuracy and effectiveness. Now let's see how we can implement a simple fast API application to serve our machine learning model for predictions. First, we import the necessary libraries, including fast API for building the web application, joblib for loading our pre-trained model, and pandas for data manipulation. Next, we instantiate a fast API application and load the model using joblib, which retrieves the saved model file from the specified directory. This is crucial as it allows our application to utilize the trained model for making predictions on incoming data. We then define an endpoint with the post method at predict, which accepts JSON data. Inside the function, we convert the received data into a pandas data frame, a format that our model can work with seamlessly. The model then generates predictions based on this input data. Finally, we ensure that the application runs with UVicorn, a lightning-fast ASGI server, allowing our fast API application to listen for incoming requests on all available IP addresses at port 8000. By setting it up this way, we create a robust interface for making predictions, ready to scale as user demand grows. Now let's see how we can implement a Dockerfile to containerize our fast API application, ensuring that it runs consistently across different environments. The first step is to choose a base image. In this case, we're using the official Python 3.8 Slim image to keep our container lightweight. Setting the working directory to app is crucial, as it defines where all subsequent commands will be executed within the container. Next, we copy the requirements .txt file into the container. This file is essential for installing the necessary packages your application needs to run. By using the run command, we execute the installation of these packages without caching to minimize the image size. After that, we copy the rest of our application code into the container, allowing it to access all necessary components. It's important to expose port 8000, as this is where our fast API app will listen for incoming requests. Finally, we specify the command to run the application using UVicorn, a lightning-fast ASGI server for Python. By following this setup, we ensure that our fast API application functions seamlessly, minimizing the risk of dependency-related issues during deployment. Now let's see how we can implement security measures for our fast API application using OAuth 2 for API authentication. The code begins by importing necessary components from the fast API library, specifically depends for dependency injection and OAuth to password bearer for managing token exchange. We define an instance of OAuth to password bearer, specifying a token URL where clients can obtain their access tokens. Next, we define a post endpoint for the prediction route using an asynchronous function named predict. The function accepts a data parameter containing the user input and a token parameter that utilizes the OAuth 2 scheme dependency. This ensures that any request made to the predict endpoint requires a valid token in the header, creating a robust layer of authentication. Before processing the input data, there would typically be a step here to validate the token to ensure that only authorized users can access this endpoint. Once the token is validated, the JSON input is transformed into a data frame, which we can use to make predictions with the pre-trained model. Finally, the function returns the predictions in a list format, encapsulating our security and functionality effectively. Next, we will implement a simple git command that allows us to roll back to a previous stable version of our deployed model. This is a crucial step in any continuous integration and deployment (CI/CD) process, as it ensures that if the newly deployed model version encounters performance issues, we can swiftly revert to a version that we know is reliable. In the code, we first indicate that we want to check out the previous version, which in this case is tagged as v10. By using the command git checkout v10, we effectively switch our current working directory's state to match that of the specified version. This operation allows access to the previous model's code and configurations, enabling us to redeploy it without the need for extensive debugging or troubleshooting. It serves as a safety net, minimizing downtime and ensuring that users continue to receive accurate predictions. After executing this command, we simply redeploy the version of the model to restore functionality until we address any issues present in the newer version. This simple yet effective rollback strategy exemplifies best practices in model deployment management. In conclusion, understanding the challenges associated with model deployment is paramount for any data scientist or machine learning engineer. Each step, from ensuring reproducibility and consistent monitoring to handling scalability, security, dependency management, and the ability to roll back, plays a critical role in the deployment process. By mastering these concepts and employing best practices in your deployment workflow, you set yourself up for success, enabling your machine learning models to not only function effectively, but provide real value in production environments. As you progress in your journey, remember that deployment is not an afterthought. It is the culmination of your hard work and insights into an operational product that can make a difference. Model deployment often presents unique challenges that must be carefully managed for success. In the field of machine learning, especially when using libraries like scikit-learn, there's quite a bit to navigate when you finally push your model into production. From model evaluation to managing data drift, each step plays a critical role in ensuring that your model performs optimally in real-world applications. Now let's implement a simple model using the iris dataset to understand how initial model performance is assessed. First, we start by importing the necessary libraries, such as pandas for data manipulation and scikit-learn for our machine learning tasks. We then load the iris dataset and convert it into a suitable format, organizing the feature data into a data frame and the target values into a series. Next, we split the dataset into training and testing sets to ensure our model is evaluated on unseen data. This separation is crucial for assessing the model's generalization capability. Following this, we instantiate a random forest classifier, which is a robust ensemble learning model known for handling various types of data effectively. After fitting the model on the training data, we generate predictions on the test set. Finally, we evaluate the model's performance by calculating the accuracy score, providing a clear metric on its ability to predict the correct classes. Now that we have a baseline accuracy, we can explore how to handle data drift by simulating changes in the input data. This will help demonstrate the need for ongoing monitoring and retraining in real-world applications. Now let's see how we can implement Lime to explain our model's predictions, enhancing interpretability. First, we begin by importing the Lime Tabular Explainer class, which will help us create an explainer that is compatible with tabular data, like our iris dataset. Next, we instantiate this explainer by passing in the training data, along with the feature names and class names relevant to our classification task. This setup allows Lime to understand our model's structure and the significance of each feature. With the explainer ready, we then select an instance from our test set that we wish to interpret. In this example, we choose the first instance, index 0, for simplicity. Using the explainInstance method, we request an explanation for this specific instance, providing the model's probability predictions as the second argument. This method analyzes how the individual features contribute to the prediction made by the model. Finally, to visualize the insights gained from Lime, we employ the Show in Notebook method. This generates an interactive display that highlights the contributions of each feature, allowing us to understand the reasoning behind the model's prediction. This powerful interpretability tool not only aids in evaluating model performance, but also fosters trust among stakeholders in real-world decision-making scenarios. Now let's implement a method for retraining our machine learning model with new data as part of our feedback loop process. Here, we assume that new incoming data is available, which we will load into a pandas data frame. This new data should closely resemble the structure of our original dataset, containing features and labels. Next, we will separate the target variable from our features, creating a new input dataset, xnew, and the corresponding target variable, ynew. With this prepared data, we will then retrain our existing model by calling the fit method, which updates the model parameters based on the new information. Once the retraining process is complete, it's crucial to evaluate the updated model's performance against our original test set. This is done by using the trained model to predict outcomes on the xtest data. The results of these predictions are compared to the true values, resulting in a new accuracy score that reflects how well the model is performing after being updated with fresh data. Finally, we print this new accuracy, which allows us to assess the effectiveness of our retraining process. This continuous evaluation ensures that our model remains responsive to changes in the underlying data patterns. Now let's implement the following code to evaluate the importance of features in our model using permutation importance, a model-agnostic method. First, we import the permutation importance function from the scikit-learn inspection module, which will allow us to assess the contribution of each feature to the model predictions. Afterward, we call this function, passing in our trained model along with the test data xtest and corresponding labels ytest, specifying the number of repeats for the importance estimation and setting a random state for reproducibility. The result of this function call stars the mean importances of each feature in the result variable. To better understand the significance of each feature, we sought the indices of the importances in ascending order. This enables us to identify which features contribute most to our model's predictions. Next, we utilize Matplotlib to visualize these importances. By creating a horizontal bar chart, we can clearly see how each feature ranks based on its calculated importance. The x-axis represents the permutation importance scores, while the y-axis lists the features, allowing for easy interpretation at a glance. By analyzing this plot, we can make informed decisions regarding which features to retain or modify in our model, thereby enhancing its performance over time. In conclusion, the evaluation of machine learning models is not a one-time task, but a continual process that must be adapted and refined. Ensuring that your models remain robust against data drift, are interpretable, benefit from feedback loops, and consider shifts in feature importance are all critical components to maintaining high performance in practical applications. As you continue to explore and implement your own models, keeping these challenges in mind will enable you to leverage machine learning effectively and responsibly. Remember, the landscape of data and machine learning is dynamic, and your approach should be adaptive just like the models you're working with. Implementing machine learning effectively requires adherence to best practices that ensure successful outcomes. In this lesson, we'll dive deep into some of the best practices for machine learning deployment using scikit-learn, so you can set your models up for success right from the beginning. So far, we learned about the ongoing challenges in machine learning model evaluation, including the need to monitor for data drift and maintain model interpretability. We discussed tools like Lime to enhance understanding of model predictions and implemented feedback loops to continuously improve performance with new data. Additionally, we highlighted the importance of assessing feature relevance over time, ensuring our models adapt to evolving data landscapes. These considerations are vital for achieving robust and effective machine learning implementations. Now, we will talk about best practices in deploying machine learning models and how implementing them can significantly enhance your model's performance. Now let's implement the following steps to set up our DVC project for versioning our datasets. We start by installing DVC using the command to manage our data effectively. This tool is instrumental in tracking changes and maintaining version control, which is essential for collaboration across teams in machine learning projects. Next, we'll initialize a new DVC project with the dvc init command. This action creates a DVC directory which will store the metadata related to our data versions, setting the stage for robust version management. After setting up the project, we can add our dataset to DVC. We use the dvc add command followed by the path to our dataset. This step registers the dataset with DVC, allowing it to track changes and maintain the integrity of the data as we work on our models. Finally, we commit these changes to Git, which includes adding the necessary DVC files to our version control system. Utilizing this git commit command with a clear message not only documents the addition of our dataset, but also integrates our DVC management with the broader versioning practices we apply to our codebase. Next, we will write a YAML configuration file, which will enable us to easily define and manage various parameters for our machine learning experiments in one central location. The configuration file, named config YAML, specifies important attributes such as the model type and its parameters, as well as the data source we will be using. In this case, we are utilizing a random forest classifier model with defined hyperparameters, like the number of estimators set to 100 and a maximum depth of 5. Additionally, it provides the path to our dataset and a split ratio for training and testing purposes. Now let's see how we can load this configuration into our Python script. We will use the YAML package to read the YAML file and load its contents into a Python dictionary. This allows us to access the model name and parameters directly within our code, ensuring that we can make changes to the configuration easily and keep our code clean. With this approach, any adjustments to model parameters can be made in one place, which significantly enhances the reproducibility and flexibility of our experiments. By adopting this practice, we lay the groundwork for structured and efficient machine learning workflows. Now let's take a look at how we can implement recursive feature elimination, RFE, using scikit-learn to enhance our model's performance through effective feature selection. We begin by importing the necessary libraries, including load Boston for the dataset, RFE for the feature elimination process, and linear regression as our model. Next, we load the Boston housing dataset, which contains various features related to housing prices. After loading our data, we instantiate a linear regression model that will be used to predict house prices. Now, we create the RFE object where we specify that we want to select the top 5 most important features. By fitting the RFE model to our dataset, RFE evaluates the significance of each feature in predicting the target variable, which allows it to determine which features to keep. Finally, we print the selected features and their ranking. The output of this step informs us which features have been identified as the most influential in predicting housing prices. This streamlined feature set not only simplifies our model, but can also improve its accuracy and interpretability, leading to more robust and reliable predictions. Now let's see how we can evaluate our model's performance using scikit-learn. We start by importing necessary libraries, including train test split to divide our dataset into training and testing sets, random forest classifier to create our model, and classification report for evaluating model predictions. Next, we load a sample dataset, in this case the iris dataset, where the feature matrix X and the target variable Y are extracted for further processing. We then implement the train test split, setting aside 20% of the data for testing while ensuring reproducibility with a random seed. With our data prepared, we proceed to train the random forest model on the training data. After fitting the model, we make predictions on the unseen test set. To assess how well our model has performed, we utilize the classification report, which provides key metrics such as precision, recall, and F1 score, enabling us to gauge the model's effectiveness in distinguishing between classes. Finally, we print this report to interpret our model's performance, reflecting the crucial role of evaluation in the model development lifecycle. Now let's see how we can implement a machine learning pipeline using scikit-learn that simplifies our workflow and enhances reproducibility. First, we import essential classes from scikit-learn, including pipeline, standard scalar, simple imputer, and logistic regression. This sets the groundwork for our pipeline, which will effectively handle missing data, scale features, and fit a logistic regression model in one go. Next, we define some sample data, where our feature matrix X contains missing values represented by NP, NaN, and the target variable Y consists of binary outcomes. The significance of this step lies in our choice to use a simple imputer, which automatically fills in missing values during the pipeline's execution, ensuring no data is lost during preprocessing. Now let's construct the pipeline by specifying a sequence of processing steps as tuples. We first impute missing values, followed by scaling the features for better model performance, and then fitting our model. Finally, after training the pipeline with the fit method, we can easily make predictions on the same input data, demonstrating the seamless integration of preprocessing and modeling within this robust pipeline structure. Now let's implement a way to monitor your machine learning model's performance over time by logging its accuracy. First, we define a simulated function called collectNewData, which generates dummy real outcomes and retrieves predictions from our model. This provides a simple way to compare what the model predicted with the actual outcomes. Next, we create the logPerformance function, which will perform the logging task. Inside this function, we call collectNewData to gather the true labels and predicted values. Using the accuracy score from scikit-learn, we calculate the accuracy of the predictions. To keep a record of these metrics, we construct a data frame with the true labels, predicted values, and the computed accuracy. This data frame is then appended to a CSV file named performance log, CSV, which allows for easy tracking over time. Finally, we print the logged accuracy to the console, providing immediate feedback on model performance. By regularly executing this logging function, we ensure that we can track model performance and address any issues promptly, maintaining a robust monitoring strategy. Finally, always remember to prepare for ethical considerations in machine learning deployment. Be mindful of bias and how data reflects certain social biases. Models deployed without careful consideration can lead to harmful or discriminatory outcomes. Evaluate your dataset for fairness and ensure that model predictions do not disproportionately affect certain groups. Real-life outcomes from machine learning models can carry significant ethical implications, spanning fields like hiring practices, loan approvals, and more. Tools like fairness indicators can help evaluate fairness across different demographic groups on your models. Incorporate ethical guidelines in your review checklist before deploying a model into production to ensure that it's not inadvertently perpetuating biases or misleading conclusions. To wrap it all up, implementing best practices in machine learning deployment is integral to crafting models that are not only effective but also sustainable and ethical. By versioning data and models, ensuring reproducibility, focusing on feature engineering, and maintaining vigilance in monitoring performance, you set up a robust framework for your machine learning workflows. Remember to always keep ethics in the forefront, continuing to adapt to the changing data landscape. Embrace these practices and watch how they elevate your machine learning projects to new. In this final section, we will do a project challenge to apply what we have learned so far. Your task is to choose a publicly available dataset from platforms like Kaggle or the UCI machine learning repository and define a clear problem to solve, whether it's classification or regression. You'll need to load and preprocess the data, handling missing values and scaling features where necessary, and split the dataset into training and testing sets. From there, select at least 2 machine learning algorithms, such as linear regression, decision trees, or support vector machines, to effectively build your model, using tools like Grid Search CV for hyperparameter tuning to enhance its accuracy. Train your models with the training data and evaluate their performance using appropriate metrics, and don't forget to visualize your findings with Matplotlib or Seaborn to make your results more insightful. Finally, compile all of this information into a comprehensive report detailing your problem statement, methodology, results, and conclusions. Remember, you can find the final project guidelines and additional resources in the GitHub repository linked in the description. Good luck, and let your creativity shine in this